following is a conversation with Stephen Wolfram, a computer scientist, mathematician, and theoretical physicist who is the founder and CEO of Wolfram Research, a company behind Mathematica, Wolfram Alpha, Wolfram Language, and the new Wolfram Physics project. He's the author of several books, including A New Kind of Science, which, on a personal note, was one of the most influential books in my journey in computer science and artificial intelligence. It made me fall in love with the mathematical beauty and power of cellular automata. It is true that perhaps one of the criticisms of Stephen is on a human level, that he has a big ego, which prevents some researchers from fully enjoying the content of his ideas. We talk about this point in this conversation. To me, ego can lead you astray, but can also be a superpower, one that fuels bold, innovative thinking that refuses to surrender to the cautious ways of academic institutions. And here, especially, I ask you to join me in looking past the peculiarities of human nature and opening your mind to the beauty of ideas in Stephen's work and in this conversation. I believe Stephen Wolfram is one of the most original minds of our time, and at the core is a kind, curious, and brilliant human being. This conversation was recorded in November 2019 when the Wolfram Physics project was underway, but not yet ready for public exploration as it is now. We now agreed to talk again, probably multiple times in the near future, so this is round one, and stay tuned for round two soon. This is the Artificial Intelligence Podcast. If you enjoy it, subscribe on YouTube, review it with 5 stars on Apple Podcast, support it on Patreon, or simply connect with me on Twitter at Lex Fridman, spelled Fridman. As usual, I'll do a few minutes of ads now, and never any ads in the middle that can break the flow of the conversation. I hope that works for you and doesn't hurt the listening experience. Quick summary of the ads. 2 sponsors, ExpressVPN and Cash App. Please consider supporting the podcast by getting ExpressVPN at expressvpn.com/LexPod and downloading Cash App and using code LEXPODCAST. This show is presented by Cash App, the #1 finance app in the App Store. When you get it, use code LEXPODCAST. Cash App lets you send money to friends, buy Bitcoin, and invest in the stock market with as little as $1. Since Cash App does fractional share trading, let me mention that the order execution algorithm that works behind the scenes to create the abstraction of fractional orders is an algorithmic marvel. So big props to the Cash App engineers for solving a hard problem that in the end provides an easy interface that takes a step up to the next layer of abstraction over the stock market. This makes trading more accessible for new investors and diversification much easier. So again, if you get Cash App from the App Store or Google Play and use the code LEXPODCAST, you get $10, and Cash App will also donate $10 to FIRST, an organization that is helping to advance robotics and STEM education for young people around the world. This show is presented by ExpressVPN. Get it at expressvpn.com/LexPod to get a discount and to support this podcast. I've been using ExpressVPN for many years. I love it. It's really easy to use. Press the big power on button and your privacy is protected. And if you like, you can make it look like your location is anywhere else in the world. This has a large number of obvious benefits. Certainly, it allows you to access international versions of streaming websites like the Japanese Netflix or the UK Hulu. ExpressVPN works on any device you can imagine. I use it on Linux. Shout out to Ubuntu. New version coming out soon, actually. Windows, Android, but it's available anywhere else too. Once again, get it at expressvpn.com/LexPod to get a discount and to support this podcast. And now, here's my conversation with Stephen Wolfram. You and your son, Christopher, helped create the alien language in the movie Arrival. So let me ask maybe a bit of a crazy question, but if aliens were to visit us on Earth, do you think we would be able to find a common language?
Well, by the time we're saying aliens are visiting us, we've already prejudiced the whole story. Because the concept of an alien actually visiting, so to speak, we already know they're kind of things that make sense to talk about visiting. So we already know they exist in the same kind of physical setup that we do. They're not, it's not just radio signals. It's an actual thing that shows up and so on. So I think in terms of, can one find ways to communicate? Well, the best example we have of this right now is AI. I mean, that's our first sort of example of alien intelligence. And the question is, how well do we communicate with AI? If you were in the middle of a neural net and you open it up and it's like, what are you thinking? Can you discuss things with it? It's not easy, but it's not absolutely impossible. So I think given the setup of your question, aliens visiting, I think the answer is yes, one will be able to find some form of communication, whatever communication means. Communication requires notions of purpose and things like this. It's a kind of philosophical quagmire.
So if AI is a kind of alien life form, what do you think visiting looks like? So if we look at aliens visiting, and we'll get to discuss computation and the world of computation, but if you were to imagine, you said you already prejudiced something by saying you visit, but how would aliens visit?
By visit, there's kind of an implication, and here we're using the imprecision of human language. In a world of the future, if that's represented in computational language, we might be able to take the concept visit and go look in the documentation basically and find out exactly what does that mean, what properties does it have, and so on. But by visit in ordinary human language, I'm kind of taking it to be there's something, a physical embodiment that shows up in a spacecraft, since we kind of know that that's necessary. We're not imagining it's just, photons showing up in a radio signal that, photons in some very elaborate pattern. We're imagining it's physical things made of atoms and so on that show up.
Can it be photons in a pattern?
Well, that's a good question. I mean, whether there is the possibility, what counts as intelligence? Good question. I mean,
Yes.
It's, and I used to think there was sort of there'll be, it'll be clear what it means to find extraterrestrial intelligence, et cetera, et cetera, et cetera. I've increasingly realized as a result of science that I've done that there really isn't a bright line between the intelligent and the merely computational, so to speak. So, in our kind of everyday sort of discussion, we'll say things like, the weather has a mind of its own. Well, let's unpack that question. We realize that there are computational processes that go on that determine the fluid dynamics of this and that in the atmosphere, et cetera, et cetera, et cetera. How do we distinguish that from the processes that go on in our brains of, the physical processes that go on in our brains? How do we separate those? How do we say the physical processes going on that represent sophisticated computations in the weather? Oh, that's not the same as the physical processes that go on that represent sophisticated computations in our brains. The answer is I don't think there is a fundamental distinction. I think the distinction for us is that there's kind of a thread of history and so on that connects kind of what happens in different brains to each other, so to speak. And it's what happens in the weather is something which is not connected by sort of a thread of civilizational history, so to speak, to what we're used to.
In the stories that the human brains told us, but maybe the weather has its own stories that it tells itself.
Absolutely. And that's where we run into trouble thinking about extraterrestrial intelligence, because, it's like that pulsar magnetosphere that's generating these very elaborate radio signals. Is that something that we should think of as being this whole civilization that's developed over the last however long, millions of years of processes going on in the neutron star or whatever, versus what we're used to in human intelligence? I mean, I think in the end, when people talk about extraterrestrial intelligence and where is it, and the whole, Fermi paradox of how come there's no other signs of intelligence in the universe, my guess is that we've got sort of two alien forms of intelligence that we're dealing with: artificial intelligence and sort of physical or extraterrestrial intelligence. And my guess is people will sort of get comfortable with the fact that both of these have been achieved around the same time. And in other words, people will say, well, yes, we're used to computers, things we've created, digital things we've created, being sort of intelligent like we are. And they'll say, oh, we're kind of also used to the idea that there are things around the universe that are kind of intelligent like we are, except they don't share the sort of civilizational history that we have, and so we don't. They're a different branch. I mean, it's similar to when you talk about life, for instance. I mean, you kind of said life form, I think, almost synonymously with intelligence, which I don't think is the AIs would be upset to hear you equate those two
because
things.
I really probably implied biological life.
Right.
But you're saying, I mean, we'll explore this more, but you're saying it's really a spectrum, and it's all just a kind of computation, and so it's a full spectrum, and we just make ourselves special by weaving a narrative around our particular kinds of computation.
Yes. I mean, the thing that I think I've kind of come to realize is, at some level, it's a little depressing to realize that there's so little that's special.
Or liberating.
Well, yeah, but I mean, it's the story of science, right? In from Copernicus on, it's like, first we were like convinced our planet's at the center of the universe.
Yes.
No, that's not true. Well, then we were convinced there's something very special about the chemistry that we have as biological organisms. No, that's not really true. And then we're still holding out that hope. Oh, this intelligence thing we have, that's really special.
Yeah.
I don't think it is. However, in a sense, as you say, it's kind of liberating for the following reason, that you realize that what's special is the details of us, not some abstract attribute that, we could wonder, oh, is something else going to come along and, also have that abstract attribute? Well, yes, every abstract attribute we have, something else has it. But the full details of our kind of history of our civilization and so on, nothing else has that. That's what, that's our story, so to speak. And that's sort of almost by definition special. So I view it as not being such a, I mean, initially I was like, this is bad. This is kind of, how can we have self-respect about the things that we do? Then I realized the details of the things we do, they are the story. Everything else is kind of a blank canvas.
So maybe on a small tangent, you just made me think of it, but what do you make of the monoliths in 2001 Space Odyssey in terms of aliens communicating with us and sparking the kind of particular intelligent computation that we humans have? Is there anything interesting to get from that sci-fi?
Yeah, I mean, I think what's fun about that is, the monoliths are these, 1 to 4 to 9 perfect cuboid things. Mm-hmm. And in the, Earth of a million years ago, or whatever they were portraying with a bunch of apes and so on, a thing that has that level of perfection seems out of place. Mm-hmm. It seems very kind of constructed, very engineered. So that's an interesting question. What is what's the techno signature, so to speak? What is it that you see it somewhere and you say, my gosh, that had to be engineered? Mm. Now, the fact is we see crystals, which are also very perfect. And, the perfect ones are very perfect. They're nice polyhedra or whatever. And so in that sense, if you say, well, it's a sign of it's a techno signature that it's a perfect, polygonal shape, polyhedral shape. That's not true. And so then it's an interesting question. What is the right signature? I mean, like, Gauss, famous mathematician, he had this idea, you should cut down the Siberian forest in the shape of sort of a typical image of the proof of the Pythagorean theorem on the grounds that, it's a kind of cool idea, it didn't get done, but, it's on the grounds that the Martians would see that and realize, gosh, there are mathematicians out there. It's kind of, it's in his theory of the world, that was probably the best advertisement for the cultural achievements of our species. But it's a reasonable question. What can you send or create that is a sign of intelligence in its creation, or even intention in its creation?
Yeah, you talk about if we were to send a beacon. Can you what should we send? Is math our greatest creation? What is our greatest creation?
I think it's a philosophically doomed issue. In other words, you send something, you think it's fantastic, but it's kind of like we are part of the universe. We make things that are, things that happen in the universe. Computation, which is sort of the thing that we are in some abstract sense using to create all these elaborate things we create, is surprisingly ubiquitous. In other words, we might have thought that, we've built this whole giant engineering stack that's led us to microprocessors, that's led us to be able to do elaborate computations. But this idea, the computations are happening all over the place. Yeah. The only question is whether there's a thread that connects our human intentions to what those computations are. Mm-hmm. And so I think this question of what do you send to kind of show off our civilization in the best possible way, I think any kind of almost random slab of stuff we've produced is about equivalent to everything else. I think it's one of these things where...
Such a non-romantic way of phrasing it. I just, sorry to interrupt, but I just talked to Anne Druyan, who's the wife of Carl Sagan. Uh-huh. And so I don't know if you're familiar with the Voyager. I mean, she was part of sending, I think, brainwaves of,
Wasn't it hers?
It was hers. Her brainwaves when she was first falling in love with Carl Sagan. Right, it's this beautiful story,
right?
that perhaps you would shut down the power of that by saying we might as well send anything else, and that's interesting. All of it is kind of an interesting, peculiar thing. That's
right. Well, I mean, I think it's kind of interesting to see on the Voyager, golden record thing. One of the things that's kind of cute about that is, it was made, when was it? In the late 70s, early 80s.
Yeah.
One of the things, it's a phonograph record, mm-hmm. Okay? And it has a diagram of how to play a phonograph record.
Yeah, it does.
And, it's kind of like, it's shocking that in just 30 years, if you show that to a random kid of today and you show them that diagram, and I've tried this experiment, they're like, I don't know what the heck this is. And the best anybody can think of is, take the whole record, forget the fact that it has some kind of helical track in it, just image the whole thing and see what's there. That's what we would do today. In only 30 years, our technology has kind of advanced to the point where the playing of a helical, mechanical track on a phonograph record is now something bizarre. So, that's a cautionary tale, I would say, in terms of the ability to make something that in detail sort of leads by the nose some, the aliens or whatever to do something. It's like, no, best you're going to do, as I say, if we were doing this today, we would not build a helical scan thing with a needle. We would just take some high-resolution imaging system and get all the bits off it and say, oh, it's a big nuisance that they put it in a helix, in a spiral. Let's just unravel the spiral and start from there.
Do you think, and this will get into trying to figure out interpretability of AI, interpretability of computation, being able to communicate with various kinds of computations. Do you think we'd be able to, if you put your alien hat on, figure out this record, how to play this record?
Well, it's a question of what one wants to do. I mean,
understand what the other party was trying to communicate, or understand anything about the other party.
What does understanding mean? I mean, that's the issue. The issue is, it's like when people were trying to do natural language understanding for computers, right? So people tried to do that for years. It wasn't clear what it meant. In other words, you take your piece of English or whatever, and you say, gosh, my computer has understood this. Okay, that's nice. What can you do with that? Well, so for example, when we built Wolfram Alpha, one of the things was it's doing question answering and so on, and it needs to do natural language understanding. The reason that I realized after the fact, the reason we were able to do natural language understanding quite well and people hadn't before, the number one thing was we had an actual objective for the natural language understanding. We were trying to turn the natural language
into computation,
into this computational language that we could then do things with. Now, similarly, when you imagine your alien, you say, okay, we're playing them the record. Did they understand it? Well, depends what you mean. If they, if there's a representation that they have, if it converts to some representation where we can say, oh yes, that's a representation that we can recognize represents understanding, then all well and good. Mm-hmm. But actually, the only ones that I think we can say would represent understanding are ones that will then do things that we humans kind of recognize as being useful to us.
Mm-hmm. Maybe trying to understand, quantify how technologically advanced this particular civilization is. So are they a threat to us from a military perspective?
Yeah,
That's
right.
probably the first kind of understanding that I would be interested in.
Gosh, that's so hard. I mean, that's like in the Arrival movie. That was sort of one of the key questions: is why are you here, so to speak?
Yeah.
And
Are you going to hurt us?
right. But even that is, it's a very unclear. It's like the are you going to hurt us? That comes back to a lot of interesting AI ethics questions, because we might make an AI that says, well, take autonomous cars, for instance. Are you going to hurt us? Well, let's make sure you only drive at precisely the speed limit, because we want to make sure we don't hurt you, so to speak, because that's and then, well, something, but you say, but actually that means I'm going to be really late for this thing. And, that sort of hurts me in some way. Mm-hmm. So it's hard to know, even the definition of what it means to hurt someone is unclear. And as we start thinking about things about AI ethics and so on, that's something one has to address.
There's always trade-offs, and that's the annoying thing about ethics.
Yeah, well, right. And I mean, I think ethics, like these other things we're talking about, is a deeply human thing. Yeah. There's no abstract, let's write down the theorem that proves that this is ethically correct. That's a meaningless idea. You have to have a ground truth, so to speak, that's ultimately sort of what humans want. And they don't all want the same thing. So that gives one all kinds of additional complexity in thinking about that.
One convenient thing in terms of turning ethics into computation, you can ask the question of what maximizes the likelihood of the survival of the species.
Yeah, that's a good existential issue. Yeah. But then when you say survival of the species, right, you might say, for example, let's say, forget about technology, just, hang out and, be happy, live our lives, go on to the next generation, go through many, many generations where, in a sense, nothing is happening. Is that okay? Is that not okay? Hard to know. In terms of, the attempt to do elaborate things and the attempt might be counterproductive for the survival of the species. Like, for instance, I mean, I think it's also a little bit hard to know. So, okay, let's take that as a sort of thought experiment. Okay, mm-hmm. You can say, well, what are the threats that we might have to survive? The supervolcano, the asteroid impact, all these kinds of things. Okay, so now we inventory these possible threats and we say, let's make our species as robust as possible relative to all these threats. I think in the end, it's sort of an unknowable thing what it takes to So given that you've got this AI and you've told it maximize the long term. What does long term mean? Does long term mean until the sun burns out? That's not going to work. Does long term mean next 1,000 years? Okay, there are probably optimizations for the next 1,000 years that. It's like if you're running a company, you can make a company be very stable for a certain period of time. Mm-hmm. Like if your company gets bought by some private investment group, then they'll you can run a company just fine for 5 years by just taking what it does and removing all R&D, and the company will burn out after a while, mm-hmm. but it'll run just fine for a little while. So if you tell the AI keep the humans okay for 1,000 years. There's probably a certain set of things that one would do to optimize that, many of which one might say, well, that would be a pretty big shame for the future of history, so to speak, for that to be what happens. But I think in the end, as you start thinking about that question, it is what you realize is there's a whole sort of raft of undecidability, computational irreducibility. In other words, one of the good things about sort of the what our civilization has gone through and what sort of we humans go through is that there's a certain computational irreducibility to it, in the sense that it isn't the case that you can look from the outside and just say, the answer is going to be this. At the end of the day, this is what's going to happen. You actually have to go through the process to find out. And I think that's both, that feels better in the sense it's not something is achieved by going through all of this, all of this process. And but it also means that telling the AI, go figure out, what will be the best outcome. Well, unfortunately, it's going to come back and say it's kind of undecidable what to do. We'd have to run all of those scenarios to see what happens. And if we want it for the infinite future, we're thrown immediately into sort of standard issues of kind of infinite computation and so on.
So yeah, even if you get that the answer to the universe and everything is 42, you still have to actually run the universe.
Yes.
To figure out
yes.
like the question, I guess, or the journey is the point.
Right. Well, I think it's saying, to summarize, this is the result of the universe.
Yeah.
If that is possible, it tells us, I mean, the whole sort of structure of thinking about computation and so on, and thinking about how stuff works. If it's possible to say, and the answer is such and such, you're basically saying there's a way of going outside the universe, and you're getting yourself into something of a sort of paradox, because you're saying, if it's knowable what the answer is, then there's a way to know it that is beyond what the universe provides. But if we can know it, then something that we're dealing with is beyond the universe. Mm-hmm. So then the universe isn't the universe, so to speak. So,
and in general, as we'll talk about, at least for our small human brains, it's hard to show the result of a sufficiently complex computation. It's hard. I mean, it's probably impossible, right? Undecidability. So, and the universe appears, by at least the poets, to be sufficiently complex that we won't be able to predict what the heck it's all going to.
Well, we better not be able to, because if we can, it kind of denies. I mean, it's we're part of the universe.
Yeah.
So what does it mean for us to predict? It means that our little part of the universe is able to jump ahead of the whole universe. And this quickly winds up. I mean, that it is conceivable. The only way we'd be able to predict is if we are so special in the universe. We are the one place where there is computation more special, more sophisticated than anything else that exists in the universe. That's the only way we would have the ability to sort of the almost theological ability, so to speak, to predict what happens in the universe, is to say somehow we're better than everything else in the universe, which I don't think is the case.
Yeah, perhaps we can detect a large number of looping patterns that reoccur throughout the universe and fully describe them, and therefore, but then it still becomes exceptionally difficult to see how those patterns interact and what kind of complexity emerges.
Look, the most remarkable thing about the universe is that it has regularity at all. Might not be the case. If you
Does it have regularity?
Absolutely. It's full of, I mean, physics is successful. It's full of laws that tell us a lot of detail about how the universe works. I mean, it could be the case that, the 10 to the 90th particles in the universe, they all do their own thing. But they don't. They all follow, we already know, they all follow basically the same physical laws. And that's a very profound fact about the universe. What conclusion you draw from that is unclear. I mean, in the early theologians, that was, exhibit number one for the existence of God.
Right.
Now, people have different conclusions about it, but the fact is, right now, I mean, I happen to be interested. Actually, I've just restarted a long-running kind of interest of mine about fundamental physics. I'm kind of like I'm on a bit of a quest, which I'm about to make more public, to see if I can actually find the fundamental theory of physics.
Excellent. We'll come to that, and I just had a lot of conversations with quantum mechanics folks, so I'm really excited on your take, because I think you have a fascinating take on the fundamental nature of our reality from a physics perspective. So, and what might be underlying the kind of physics as we think of it today. Okay, let's take a step back. What is computation?
It's a good question. Operationally, computation is following rules. That's kind of it. I mean, computation is the process of systematically following rules, and it is the thing that happens when you do that.
So taking initial conditions or taking inputs and following rules. I mean, what are you following rules on? So there has to be some data,
Not necessarily. It can be something where there's a very simple input, and then you're following these rules, and you'd say there's not really much data going into this. You could actually pack the initial conditions into the rule if you want to. So I think the question is there a robust notion of computation? That is,
What does robust mean?
what I mean by that is something like this. So one of the things in an area of physics, something like energy. Okay, there are different forms of energy. But somehow energy is a robust concept that isn't particular to kinetic energy or nuclear energy or whatever else. There's a robust idea of energy. So one of the things you might ask is the robust idea of computation? Or does it matter that this computation is running in a Turing machine? This computation is running in a CMOS silicon CPU. This computation is running in a fluid system in the weather. Those kinds of things. Or is there a robust idea of computation that transcends the sort of detailed framework that it's running in? Okay, and
is there?
Yes. I mean, it wasn't obvious that there was, so it's worth understanding the history and how we got to where we are right now, because to say that there is a statement in part about our universe. It's not a statement about what is mathematically conceivable. It's about what actually can exist for us.
Maybe you can also comment, because energy as a concept is robust, but there's also its intricate, complicated relationship with matter, with mass, is very interesting, of particles that carry force and particles that carry force and particles that have mass. These kinds of ideas, they seem to map to each other, at least in the mathematical sense. Is there a connection between energy and mass and computation, or are these completely disjoint ideas?
We don't know yet. The things that I'm trying to do about fundamental physics may well lead to such a connection, but there is no known connection at this time.
So can you elaborate a little bit more on how do you think about computation? What is computation?
Yeah, so I mean, let's tell a little bit of a historical story.
Yes.
Okay. So, go back 150 years, people were making mechanical calculators of various kinds. And, the typical thing was, you want an adding machine, you go to the adding machine store, basically. You want a multiplying machine, you go to the multiplying machine store. They're different pieces of hardware. And so that means that at least at the level of that kind of computation and those kinds of pieces of hardware, there isn't a robust notion of computation. There's the adding machine kind of computation, there's the multiplying machine notion of computation, and they're disjoint. So what happened in around 1900, people started imagining, particularly in the context of mathematical logic, could you have something which would represent any reasonable function, right? And they came up with things. This idea of primitive recursion was one of the early ideas, and it didn't work. There were reasonable functions that people could come up with that were not represented using the primitives of primitive recursion. Okay, so then along comes 1931 and Gödel's theorem and so on. And as in looking back, one can see that as part of the process of establishing Gödel's theorem, Gödel basically showed how you could compile arithmetic, how you could basically compile logical statements like this statement is unprovable into arithmetic. So what he essentially did was to show that arithmetic can be a computer in a sense that's capable of representing all kinds of other things. And then Turing came along in 1936, came up with Turing machines. Meanwhile, Alonzo Church had come up with lambda calculus. And the surprising thing that was established very quickly is the Turing machine idea about what computation might be is exactly the same as the lambda calculus idea of what computation might be. And then there started to be other ideas, register machines, other kinds of representations of computation. And the big surprise was they all turned out to be equivalent. So in other words, it might have been the case, like those old adding machines and multiplying machines, that Turing had his idea of computation, Church had his idea of computation, and they were just different. But it isn't true. They're actually all equivalent. So then by, I would say, the 1970s or so, in sort of the computer science, computation theory area, people had sort of said, Turing machines are kind of what computation is. Physicists were still holding out, saying, no, that's just not how the universe works. We've got all these differential equations. We've got all these real numbers that have infinite numbers of digits.
Yeah, the universe is not a Turing machine.
Right. The Turing machines are a small subset of that are the things that we make in microprocessors and engineering structures and so on. So probably actually through my work in the 1980s about sort of the relationship between computation and models of physics, it became a little less clear that there was this big sort of dichotomy between what can happen in physics and what happens in things like Turing machines. And I think probably by now, people would mostly think, and by the way, brains were another kind of element of this. I mean, Gödel didn't think that his notion of computation, or what amounted to his notion of computation, would cover brains. And Turing wasn't sure either. But although he got to be a little bit more convinced that it should cover brains. But I would say by probably sometime in the 1980s, there was beginning to be sort of a general belief that, yes, this notion of computation that could be captured by things like Turing machines was reasonably robust. Now, the next question is, okay, you can have a universal Turing machine that's capable of being programmed to do anything that any Turing machine can do. This idea of universal computation, it's an important idea, this idea that you can have one piece of hardware and program it with different pieces of software. That's kind of the idea that launched most modern technology. I mean, that's the idea that launched computer revolution, software, et cetera. So important idea. Yep. But the thing that's still kind of holding out from that idea is, okay, there is this universal computation thing, but seems hard to get to. Seems like you want to make a universal computer, you have to kind of have a microprocessor with, 1 million gates in it, and you have to go to a lot of trouble to make something that achieves that level of computational sophistication. Okay, so the surprise for me was that stuff that I discovered in the early 80s, looking at these things called cellular automata, which are really simple computational systems. The thing that was a big surprise to me was that even when their rules were very, very simple, they were doing things that were as sophisticated as they did even when their rules were much more complicated. So it didn't look like, this idea, to get sophisticated computation, you have to build something with very sophisticated rules. That idea didn't seem to pan out. And instead, it seemed to be the case that sophisticated computation was completely ubiquitous, even in systems with incredibly simple rules. And so that led to this thing that I call the principle of computational equivalence, which basically says when you have a system that follows rules of any kind, then whenever the system isn't doing things that are in some sense obviously simple, then the computation that the behavior of the system corresponds to is of equivalent sophistication. So that means that when you kind of go from the very, very, very simplest things you can imagine, then quite quickly you hit this kind of threshold above which everything is equivalent in its computational sophistication. Not obvious that would be the case. I mean, that's a science fact. Well,
No. Hold on a second. You've opened with a new kind of science. I remember it was a huge eye opener. That such simple things can create such complexity, and yes, there's an equivalence, but it's not a fact. It just appears to. It's as much as a fact as sort of these theories are so elegant that it seems to be the way things are. But let me ask, sort of, you just brought up previously kind of like the communities of computer scientists with their Turing machines, the physicists with their universe, and the whoever the heck, maybe neuroscientists looking at the brain. What's your sense in the equivalence? So you've shown through your work that simple rules can create equivalently complex Turing machine systems, right? Is the universe equivalent to the kinds of to Turing machines? Is the human brain a kind of Turing machine? Do you see those things basically blending together, or is there still a mystery about how disjoint they are?
Well, my guess is that they all blend together, but we don't know that for sure yet. I mean, I should say, I said rather glibly that the principle of computational equivalence is sort of a science fact, and
yes.
I was using air quotes, quotes for the science fact, because when it is a, just to talk about that for a second, and then we'll the thing is that it is it has a complicated epistemological character, similar to things like the second law of thermodynamics, the law of entropy increase. What is the second law of thermodynamics? Is it a law of nature? Is it a thing that is true of the physical world? Is it something which is mathematically provable? Is it something which happens to be true of the systems that we see in the world? Is it, in some sense, a definition of heat, perhaps? Well, it's a combination of those things. And it's the same thing with the principle of computational equivalence. And in some sense, the principle of computational equivalence is at the heart of the definition of computation, because it's telling you there is a robust notion that is equivalent across all these systems and doesn't depend on the details of each individual system. And that's why we can meaningfully talk about a thing called computation. And we're not stuck talking about, there's computation in Turing machine number 3785, and et cetera, et cetera, et cetera. That's why there is a robust notion like that. Now, on the other hand, can we prove the principle of computational equivalence? Can we prove it as a mathematical result? Well, the answer is, actually, we've got some nice results along those lines that say, throw me a random system with very simple rules. Well, in a couple of cases, we now know that even the very simplest rules we can imagine of a certain type are universal and do sort of follow what you would expect from the principle of computational equivalence. So that's a nice piece of sort of mathematical evidence for the principle of computational equivalence.
Just to link on that point, the simple rules creating sort of these complex behaviors, but is there a way to mathematically say that this behavior is complex? That you mentioned that you cross a threshold.
Right. There are various indicators. So, for example, one thing would be, is it capable of universal computation? That is, given the system, do there exist initial conditions for the system that can be set up to essentially represent programs to do anything you want, to compute primes, to compute pi, to do whatever you want, right? So that's an indicator. So we know in a couple of examples that, yes, the simplest candidates that could conceivably have that property do have that property. And that's what the principle of computational equivalence might suggest. Yes. But this principle of computational equivalence, one question about it is it true for the physical world? Right? It might be true for all these things we come up with, the Turing machines, the cellular automata, whatever else. Is it true for our actual physical world? Is it true for the brains, which are an element of the physical world? We don't know for sure, and that's not the type of question that we will have a definitive answer to, because there's a sort of scientific induction issue. You can say, well, it's true for all these brains, but this person over here is really special, and it's not true for them. And you can't, the only way that cannot be what happens is if we finally nail it and actually get a fundamental theory for physics, and it turns out to correspond to, let's say, a simple program. If that is the case, then we will basically have reduced physics to a branch of mathematics, in the sense that we will not be, right now with physics, we're like, well, this is the theory that, this is the rules that apply here, but in the middle of that, right by that black hole, maybe these rules don't apply and something else applies, and there may be another piece of the onion that we have to peel back. But if we can get to the point where we actually have, this is the fundamental theory of physics, here it is, it's this program, run this program and you will get our universe, then we've kind of reduced the problem of figuring out things in physics to a problem of doing some, what turns out to be very difficult, irreducibly difficult mathematical problems. But it no longer is the case that we can say, that somebody can come in and say, whoops, you were right about all these things about Turing machines, but you're wrong about the physical universe. We know there's sort of ground truth about what's happening in the physical universe. Now, I happen to think, you asked me at an interesting time, because I'm just in the middle of starting to re-energize my project to kind of study the fundamental theory of physics. As of today, I'm very optimistic that we're actually going to find something, and that it's going to be possible to see that the universe really is computational in that sense. But I don't know, because we're betting against we're betting against the universe, so to speak. And I didn't, it's not like, when I spend a lot of my life building technology and then I know what's in there, right? And it may have unexpected behavior, it may have bugs, things like that, but fundamentally I know what's in there. For the universe, I'm not in that position, so to speak.
What kind of computation do you think the fundamental laws of physics might emerge from? So just to clarify, so you've done a lot of fascinating work with kind of discrete kinds of computation that, because cellular automata, and we'll talk about it, have this very clean structure. It's such a nice way to demonstrate that simple rules can create immense complexity. But what is that actually, are cellular automata sufficiently general to describe the kinds of computation that might create the laws of physics? Can you give a sense of what kind of computation do you think would create laws of physics?
So this is a slightly complicated issue because as soon as you have universal computation, you can in principle simulate anything with anything.
Right.
But it is not a natural thing to do. And if you're asking, were you to try to find our physical universe by looking at possible programs in the computational universe of all possible programs, would the ones that correspond to our universe be small and simple enough that we might find them by searching that computational universe? We got to have the right basis, so to speak. We got to have the right language, in effect, for describing computation for that to be feasible. So the thing that I've been interested in for a long time is, what are the most structureless structures that we can create with computation? So, in other words, if you say a cellular automaton, it has a bunch of cells that are arrayed on a grid, and it's very, and every cell is updated in synchrony at a particular, when there's a click of a clock, so to speak, and it goes a tick of a clock, and every cell gets updated at the same time. That's a very specific, very rigid kind of thing. But my guess is that when we look at physics and we look at things like space and time, that what's underneath space and time is something as structureless as possible. That what we see, what emerges for us as physical space, for example, comes from something that is sort of arbitrarily unstructured underneath. And so I've been for a long time interested in kind of what are the most structureless structures that we can set up. And actually what I had thought about for ages is using graphs, networks, where essentially, so let's talk about space, for example. Mm-hmm. So what is space? Is a kind of a question one might ask. Back in the early days of quantum mechanics, for example, people said, oh, for sure, space is going to be discrete because all these other things we're finding are discrete. But that never worked out in physics. And so space in physics today is always treated as this continuous thing, just like Euclid imagined it. Mm-hmm. I mean, the very first thing Euclid says in his sort of common notions is, a point is something which has no part. In other words, there are points that are arbitrarily small. Mm-hmm. And there's a continuum of possible positions of points. And the question is that true? And so, for example, if we look at, a fluid like air or water, we might say, oh, it's a continuous fluid. We can pour it. We can do all kinds of things continuously. But actually, we know, because we know the physics of it, that it consists of a bunch of discrete molecules bouncing around. And only in the aggregate is it behaving like a continuum. And so the possibility exists that that's true of space too. People haven't managed to make that work with existing frameworks in physics, but I've been interested in whether one can imagine that underneath space and also underneath time is something more structureless. And the question is it computational? So there are a couple of possibilities. It could be computational, somehow fundamentally equivalent to a Turing machine, or it could be fundamentally not. So how could it not be? It could not be. So a Turing machine essentially deals with integers, whole numbers, some level. And, it can do things like it can add 1 to a number. It can do things like this.
It can also store whatever the heck it did.
Yes, right? So it has an infinite storage. But what when one thinks about doing physics or sort of idealized physics or idealized mathematics, one can deal with real numbers with an infinite number of digits. Yeah. Numbers which are absolutely precise, and one can say, we can take this number and we can multiply it by itself.
Are you comfortable with infinity in this context? Are you comfortable in the context of computation? Do you think infinity plays a part?
I think that the role of infinity is complicated. Infinity is useful in conceptualizing things. It's not actualizable. Almost by definition, it's not actualizable.
But do you think infinity is part of the thing that might underlie the laws of physics?
I think that, no. I think there are many questions that you might ask about physics, which inevitably involve infinity. Like when you say, is faster than light travel possible? You could say, given the laws of physics, can you make something even arbitrarily large, even quotes infinitely large, that that will make faster than light travel possible? Then you're thrown into dealing with infinity as a kind of theoretical question. But I mean, talking about sort of what's underneath space and time and how one can make a computational infrastructure. One possibility is that you can't make a computational infrastructure in a Turing machine sense, that you really have to be dealing with precise real numbers. You're dealing with partial differential equations, which have precise real numbers at arbitrarily closely separated points. You have a continuum for everything. Could be that's what happens, that there's sort of a continuum for everything and precise real numbers for everything. And then the things I'm thinking about are wrong. And that's the risk you take if you're trying to sort of do things about nature, is you might just be wrong. It's for me personally, it's kind of a strange thing, because I've spent a lot of my life building technology where you can do something that nobody cares about, but you can't be sort of wrong in that sense. In the sense you build your technology and it does what it does. Yeah. But I think this question of what the sort of underlying computational infrastructure for the universe might be. Yes. It's sort of inevitable it's going to be fairly abstract, because if you're going to get all these things, like there are 3 dimensions of space, there are electrons, there are muons, there are quarks, there are this. You don't get to, if the model for the universe is simple, you don't get to have sort of a line of code for each of those things. You don't get to have sort of the muon case, the tau lepton case, and so on.
Those all have to be emergent somehow.
Right. So
something deeper.
Right. So that means it's sort of inevitable. It's a little hard to talk about what the sort of underlying structureless structure actually is.
Do you think our human beings have the cognitive capacity to understand, if we're to discover it, to understand the kinds of simple structure from which these laws can emerge? Like, do you think
that's
it's
a good
hopeless
question.
pursuit?
Well, here's what I think. I think that, I'm right in the middle of this right now.
Right.
So I'm telling you that
think you'll hit a wall?
Yeah, this human has a hard time understanding,
Yes.
A bunch of the things that are going on. But what happens in understanding is one builds waypoints. I mean, if you said, understand modern 21st century mathematics, starting from, counting back in, whenever counting was invented, 50,000 years ago, whatever it was, right? That will be really difficult. But what happens is we build waypoints that allow us to get to higher levels of understanding. And we see the same thing happening in language. When we invent a word for something, it provides kind of a cognitive anchor, a kind of a waypoint that lets us, like a podcast or something. You could be explaining, well, it's a thing which works this way, that way, the other way. But as soon as you have the word podcast and people kind of societally understand it, you start to be able to build on top of that. And so I think, and that's kind of the story of science, actually, too. I mean, science is about building these kind of waypoints where we find this sort of cognitive mechanism for understanding something, then we can build on top of it. We have the idea of, differential equations. We can build on top of that. We have this idea, that idea. So my hope is that if it is the case that we have to go all the way sort of from the sand to the computer and there's no waypoints in between, then we're toast. We won't be able to do that.
Well, eventually we might. So if we're us clever apes are good enough at building those abstractions, eventually from sand we'll get to the computer, right? And it just might be a longer journey.
The question is whether it is something that you asked, whether our human brains will quotes understand what's going on. And that's a different question, because for that, it requires steps that are sort of from which we can construct a human understandable narrative. And that's something that I think I am somewhat hopeful that will be possible. Mm-hmm. Although, as of literally today, if you ask me, I'm confronted with things that I don't understand very well.
So this is a small pattern in a computation trying to understand the rules under which the computation functions. And it's an interesting possibility under which kinds of computations such a creature can understand itself.
My guess is that so we didn't talk much about computational irreducibility, but it's a consequence of this principle of computational equivalence. And it's sort of a core idea that one has to understand, I think, which is, the question is, you're doing a computation, you can figure out what happens in the computation just by running every step in the computation and seeing what happens. Or you can say, let me jump ahead and figure out, have something smarter that figures out what's going to happen before it actually happens. And a lot of traditional science has been about that act of computational reducibility. Yes. It's like we've got these equations and we can just solve them and we can figure out what's going to happen. We don't have to trace all of those steps. We just jump ahead because we've solved these equations. Okay, so one of the things that is a consequence of the principle of computational equivalence is you don't always get to do that. Many, many systems will be computationally irreducible in the sense that the only way to find out what they do is just follow each step and see what happens. Yeah. Why is that? Well, if you're saying, well, we, with our brains, we're a lot smarter. We don't have to mess around like the little cellular automaton going through and updating all those cells. We can just, use the power of our brains to jump ahead. But if the principle of computational equivalence is right, that's not going to be correct because it means that there's us doing our computation in our brains, there's a little cellular automaton doing its computation, and the principle of computational equivalence says these two computations are fundamentally equivalent. So that means we don't get to say we're a lot smarter than the cellular automaton and jump ahead because we're just doing computation that's of the same sophistication as the cellular automaton itself.
That's computational reducibility. It's fascinating, but and that's a really powerful idea. I think that's both depressing and humbling and so on, that we in a cellular automata are the same. But the question, we're talking about the fundamental laws of physics, is kind of the reverse question. You're not predicting what's going to happen. You have to run the universe for that. But saying, can I understand what rules likely generated me?
I understand. But the problem is, to know whether you're right, you have to have some computational reducibility because we are embedded in the universe. If the only way to know whether we get the universe is just to run the universe, we don't get to do that because it just ran for 14.6 billion years or whatever. And we can't rerun it, so to speak. So we have to hope that there are pockets of computational reducibility sufficient to be able to say, yes, I can recognize those are electrons there. Yeah. And I think that it's a feature of computational irreducibility. It's sort of a mathematical feature that there are always an infinite collection of pockets of reducibility. Yeah. The question of whether they land in the right place and whether we can sort of build a theory based on them is unclear. But to this point about whether we, as observers in the universe, built out of the same stuff as the universe, can figure out the universe, so to speak, that relies on these pockets of reducibility. Without the pockets of reducibility, it won't work, can't work. But I think this question about how observers operate, it's one of the features of science over the last 100 years particularly, has been that every time we get more realistic about observers, we learn a bit more about science. So, for example, relativity was all about observers don't get to say when, what's simultaneous with what. They have to just wait for the light signal to arrive to decide what's simultaneous. Or, for example, in thermodynamics, observers don't get to say the position of every single molecule in a gas. They can only see the kind of large-scale features, and that's why the second law of thermodynamics, law of entropy increase, and so on works. If you could see every individual molecule, you wouldn't conclude something about thermodynamics. You would conclude, these molecules are just all doing these particular things. You wouldn't be able to see this aggregate fact. So I strongly expect that, and in fact, in the theories that I have, that one has to be more realistic about the computation and other aspects of observers in order to actually make a correspondence between what we experience. In fact, we have my little team and I have a little theory right now about how quantum mechanics may work, which is a very wonderfully bizarre idea about how the sort of thread of human consciousness relates to what we observe in the universe. But there's several steps to explain what that's about.
What do you make of the mess of the observer at the lower level of quantum mechanics? Sort of the textbook definition with quantum mechanics kind of says that there's two worlds. One is the world that actually is, and the other is that's observed. What do you make sense of that kind of observer?
I think actually the ideas we've recently had might actually give away into this. And that's, I don't know yet. I mean, I think it's a mess. I mean, the fact is one of the things that's interesting. And when people look at these models that I started talking about 30 years ago now, they say, oh, no, that can't possibly be right. What about quantum mechanics, right? You say, okay, tell me what is the essence of quantum mechanics? What do you want me to be able to reproduce to know that I've got quantum mechanics, so to speak? Well, and that question comes up very operationally, actually, because we've been doing a bunch of stuff with quantum computing. And there are all these companies that say, we have a quantum computer. And we say, let's connect to your API and let's actually run it. And they're like, well, maybe you shouldn't do that yet. We're not quite ready yet. And one of the questions that I've been curious about is, if I have 5 minutes with a quantum computer, how can I tell if it's really a quantum computer or whether it's a simulator at the other end, right? And turns out it's really hard. It turns out there isn't. It's like a lot of these questions about sort of what is intelligence, what's life.
That's a Turing test for a quantum computer.
That's right. That's right. It's like, are you really a quantum computer? And I think
a simulation.
Yes, exactly. Is it just a simulation, or is it really a quantum computer? Same issue all over again.
Yeah.
But that this whole issue about the sort of mathematical structure of quantum mechanics and the completely separate thing that is our experience, in which we think definite things happen, whereas quantum mechanics doesn't say definite things ever happen. Mm-hmm. Quantum mechanics is all about the amplitudes for different things to happen, but yet our thread of consciousness operates as if definite things are happening.
To linger on the point, you've kind of mentioned the structure that could underlie everything, and this idea that it could perhaps have something like a structure of a graph. Mm-hmm. Can you elaborate why your intuition is that there's a graph structure of nodes and edges and what it might represent?
Right. Okay. So the question is, what is, in a sense, the most structureless structure you can imagine? Right? So, and in fact, what I've recently realized in the last year or so, I have a new most structureless structure.
By the way, the question itself is a beautiful one and a powerful one in itself. So even without an answer, just the question is a really strong question.
Right.
But what's your new idea?
Well, it has to do with hypergraphs. Essentially, what is interesting about the sort of model I have now is it's a little bit like what happened with computation. Everything that I think of as, oh, well, maybe the model is this, I discover it's equivalent. And that's quite encouraging, because it's like I could say, well, I'm going to look at trivalent graphs with 3 edges for each node and so on. Or I could look at this special kind of graph, or I could look at this kind of algebraic structure. And turns out that the things I'm now looking at, everything that I've imagined that is a plausible type of structureless structure is equivalent to this. So what is it? Well, a typical way to think about it is, so you might have some collection of tuples, collection of let's say numbers. So you might have 1, 3, 5, 2, 3, 4, little just collections of numbers, triples of numbers, let's say, quadruples of numbers, pairs of numbers, whatever. And you have all these sort of floating little tuples. They're not in any particular order. And that sort of floating collection of tuples, and I told you this was abstract, represents the whole universe. The only thing that relates them is when a symbol is the same, it's the same, so to speak. So if you have 2 tuples and they contain the same symbol, let's say at the same position of the tuple, at the first element of the tuple, then that represents a relation. Okay, so let me try and peel this back.
Wow. Okay, so
I told you it's abstract, but this is
so the relationship is formed by some aspect of sameness.
Right, but so think about it in terms of a graph.
Yeah.
So a graph, a bunch of nodes. Let's say you number each node. Okay, then what is a graph? A graph is a set of pairs that say this node has an edge connecting it to this other node. So and a graph is just a collection of those pairs that say this node connects to this other node. So this is a generalization of that, in which instead of having pairs, you have arbitrary n tuples. That's it. That's the whole story. And now the question is, okay, so that might represent the state of the universe. How does the universe evolve? What does the universe do? And so the answer is that what I'm looking at is transformation rules on these hypergraphs. In other words, you say this whenever you see a piece of this hypergraph that looks like this, turn it into a piece of hypergraph that looks like this. Mm-hmm. So on a graph, it might be when you see the subgraph, when you see this thing with a bunch of edges hanging out in this particular way, then rewrite it as this other graph. Mm-hmm. Okay? And so that's the whole story. So the question is, so now you say, I mean, as I say, this is quite abstract. And one of the questions is, where do you do those updating? So you've got this giant graph.
What triggers the updating? Like, what's the ripple effect of it? Is it?
Yes.
And I suspect everything's discrete, even in time. So.
Okay, so the question is, where do you do the updates?
Yes.
And the answer is, the rule is you do them wherever they apply. And you do them, the order in which the updates is done is not defined. That is, you can do them, so there may be many possible orderings for these updates. Now, the point is, imagine you're an observer in this universe. Mm-hmm. So, and you say, did something get updated? Well, you don't in any sense know until you yourself have been updated.
Right.
So, in fact, all that you can be sensitive to is essentially the causal network of how an event over there affects an event that's in you.
That doesn't even feel like observation. That's something else. You're just part of the whole thing.
Yes, you're part of it. But even to have, so the end result of that is all you're sensitive to is this causal network of what event affects what other event. I'm not making a big statement about sort of the structure of the observer. I'm simply saying, I'm simply making the argument that what happens, the microscopic order of these rewrites is not something that any observer, any conceivable observer in this universe can be affected by. Because the only thing the observer can be affected by is this causal network of how the events in the observer are affected by other events that happen in the universe. So the only thing you have to look at is the causal network. You don't really have to look at this microscopic rewriting that's happening. So these rewrites are happening wherever they happen wherever they feel like.
Causal network. Is there, you said that there's not really, so the idea would be an undefined, like what gets updated, the sequence of things is undefined. It's
yes.
That's what you mean by the causal network. But then the
causal network is, given that an update has happened, that's an event. Then the question is that event causally related to? Does that event, if that event didn't happen, then some future event couldn't happen yet.
Gotcha.
And so you build up this network of what affects what. Yeah. Okay? And so what that does, so when you build up that network, that's kind of the observable aspect of the universe in some sense.
Gotcha.
And so then you can ask questions about, how robust is that observable network of what's happening in the universe? Okay, so here's where it starts getting kind of interesting. So for certain kinds of microscopic rewriting rules, the order of rewrites does not matter to the causal network. And so this is, mathematical logic, moment. This is equivalent to the Church-Rosser property or the confluence property of rewrite rules. And it's the same reason that if you're simplifying an algebraic expression, for example, you can say, let me expand those terms out, let me factor those pieces. Doesn't matter what order you do that in, you'll always get the same answer. And it's the same fundamental phenomenon that causes, for certain kinds of microscopic rewrite rules, that causes the causal network to be independent of the microscopic order of rewritings.
Why is that property important?
Because it implies special relativity. I mean, the reason it's important is that property, special relativity says you can look at these you can look at different reference frames. You can be looking at your notion of what's space and what's time can be different, depending on whether you're traveling at a certain speed, depending on whether you're doing this, that, and the other. But nevertheless, the laws of physics are the same. That's what the principle of special relativity says, is the laws of physics are the same, independent of your reference frame. Well, turns out this sort of change of the microscopic rewriting order is essentially equivalent to a change of reference frame, or at least there's a sub-part of how that works that's equivalent to change of reference frame. So, somewhat surprisingly, and sort of for the first time in forever, it's possible for an underlying microscopic theory to imply special relativity, to be able to derive it. It's not something you put in as it's something where this other property, causal invariance, which is also the property that implies that there's a single thread of time in the universe. It might not be the case. That's what would lead to the possibility of an observer thinking that definite stuff happens. Otherwise, you've got all these possible rewriting orders, and who's to say which one occurred? But with this causal invariance property, there's a notion of a definite thread of time.
It sounds like that kind of idea of time, even space, would be emergent from the system.
Oh, yeah. No, I mean,
so it's not a fundamental part of the system.
No, the fundamental level, all you've got is a bunch of nodes connected by hyperedges or whatever.
So there's no time, there's no space.
That's right. But the thing is that it's just like imagine you're just dealing with a graph. And imagine you have something like a honeycomb graph where you have a bunch of hexagons. That graph at a microscopic level, it's just a bunch of nodes connected to other nodes. But at a macroscopic level, you say that looks like a honeycomb, lattice. It looks like a two-dimensional, manifold of some kind. It looks like a two-dimensional thing. If you connect it differently, if you just connect all the nodes one to another in kind of a sort of linked list type structure, then you'd say, well, that looks like a one-dimensional space. But at the microscopic level, all these are just networks with nodes. The macroscopic level, they look like something that's like one of our sort of familiar kinds of space. And it's the same thing with these hypergraphs. Now, if you ask me, have I found one that gives me three-dimensional space? The answer is not yet. So we don't know. This is one of these things we're kind of betting against nature, so to speak. Right. And I have no way to know. I mean, so there are many other properties of this kind of system that are very beautiful, actually, and very suggestive. And it will be very elegant if this turns out to be right, because it's very clean. I mean, you start with nothing, and everything gets built up. Everything about space, everything about time, everything about matter. It's all just emergent from the properties of this extremely low-level system. And that will be pretty cool if that's the way our universe works. Now, on the other hand, the thing that I find very confusing is, let's say we succeed. Let's say we can say this particular sort of hypergraph rewriting rule gives the universe. Just run that hypergraph rewriting rule for enough times and you'll get everything. You'll get this conversation we're having. You'll get everything. If we get to that point and we look at what is this thing, what is this rule that we just have that is giving us our whole universe, how do we think about that thing? Let's say, turns out the minimal version of this, and this is kind of cool thing for a language designer like me, the minimal version of this model is actually a single line of Wolfram Language code. So that's, which I wasn't sure was going to happen that way, but it's kind of no, we don't know what that's just the framework. To know the actual particular hypergraph, it might be a longer, the specification of the rules might be slightly longer.
How does that help you accept marveling in the beauty and the elegance of the simplicity that creates the universe? Does that help us predict anything? Not really, because of the irreducibility.
That's correct. But so the thing that is really strange to me, and I haven't wrapped my brain around this yet, is, one keeps on realizing that we're not special, in the sense that, we don't live at the center of the universe, we don't blah, blah, blah. And yet, if we produce a rule for the universe and it's quite simple, and we can write it down in a couple of lines or something, that feels very special. How do we come to get a simple universe when many of the available universes, so to speak, are incredibly complicated, might be, a quintillion characters long? Why did we get one of the ones that's simple? And so I haven't wrapped my brain around that issue yet.
If indeed we are in such a the universe is such a simple rule, is it possible that there is something outside of this, that we are in a kind of what people call the simulation, right? That we're just part of a computation that's being explored by a graduate student in an alternate universe?
Well, the problem is we don't get to say much about what's outside our universe, because by definition, our universe is what we exist within.
Yeah.
Now, can we make a sort of almost theological conclusion from being able to know how our particular universe works? Interesting question. I don't think that if you ask the question, could we, and it relates again to this question about the extraterrestrial intelligence, we've got the rule for the universe. Was it built in on purpose? Hard to say. That's the same thing as saying we see a signal from, that we're, receiving from some, random star somewhere, and it's a series of pulses, and, it's a periodic series of pulses, let's say. Was that done on purpose? Can we conclude something about the origin of that series of pulses?
Just because it's elegant does not necessarily mean that somebody created it, or that we can even comprehend.
Yeah, I think it's the ultimate version of the sort of identification of the technosignature question. It's the ultimate version of that. Was our universe a piece of technology, so to speak? And how on earth would we know? It's in the kind of crazy science fiction thing you could imagine, you could say, oh, somebody's going to have, there's going to be a signature there. It's going to be, made by so-and-so. But there's no way we could understand that, so to speak. And it's not clear what that would mean, because the universe simply, if we find a rule for the universe, we're simply saying that rule represents what our universe does. We're not saying that rule is something running on a big computer and making our universe. It's just saying that represents what our universe does, in the same sense that, laws of classical mechanics, differential equations, whatever they are, represent what mechanical systems do. It's not that the mechanical systems are somehow running solutions to those differential equations. Those differential equations are just representing the behavior of those systems.
So what's the gap, in your sense, to linger on the fascinating, perhaps slightly sci-fi question? What's the gap between understanding the fundamental rules that create a universe and engineering a system, actually creating a simulation ourselves? So you've talked about nano engineering, kind of ideas that are kind of exciting, actually creating some ideas of computation in the physical space. How hard is it as an engineering problem to create the universe once you know the rules that create it?
Well, that's an interesting question. I think the substrate on which the universe is operating is not a substrate that we have access to. I mean, the only substrate we have is that same substrate that the universe is operating in. So if the universe is a bunch of hypergraphs being rewritten, then we get to attach ourselves to those same hypergraphs being rewritten. We don't get to, and if you ask the question, is the code clean? Can we write nice, elegant code with efficient algorithms and so on? Well, that's an interesting question. That's this question of how much computational reducibility there is in the system.
But so I've seen some beautiful cellular automata that basically create copies of itself within itself, right? So that's the question, whether it's possible to create, like whether you need to understand the substrate or whether you can just...
Yeah, well, right. I mean, so one of the things that is sort of one of my slightly sci-fi thoughts about the future, so to speak, is, right now, if you poll typical people who say, do you think it's important to find the fundamental theory of physics? You get, because I've done this poll, informally at least, it's curious actually, you get a decent fraction of people saying, oh yeah, that would be pretty interesting.
I think that's becoming, surprisingly enough, more, if a lot of people are interested in physics in a way that, like, without understanding it, just kind of watching scientists, a very small number of them, struggle to understand the nature of our reality.
Right. I think that's somewhat true. And in fact, in this project that I'm launching into to try and find the fundamental theory of physics, I'm going to do it as a very public project. I mean, it's going to be live streamed and all this kind of stuff. And I don't know what will happen. It'll be kind of fun. I think that it's the interface to the world of this project. I figure one feature of this project is, unlike technology projects that basically are what they are, this is a project that might simply fail, because it might be the case that it generates all kinds of elegant mathematics that has absolutely nothing to do with the physical universe that we happen to live in. Well, okay, so we're talking about kind of the quest to find the fundamental theory of physics. First point is, it's turned out it's kind of hard to find the fundamental theory of physics. People weren't sure that that would be the case. Back in the early days of applying mathematics to science, 1600s and so on, people were like, oh, in 100 years, we'll know everything there is to know about how the universe works. Turned out to be harder than that. And people got kind of humble at some level, because every time we got to sort of a greater level of smallness in studying the universe, it seemed like the math got more complicated and everything got harder. When I was a kid, basically, I started doing particle physics. And, when I was doing particle physics, I always thought finding the fundamental theory of physics, that's a kooky business. We'll never be able to do that. But we can operate within these frameworks that we built for doing quantum field theory and general relativity and things like this. And it's all good, and we can figure out a lot of stuff.
Did you even at that time have a sense that there's something behind that too?
Sure. I just didn't expect that. I thought in some rather it's actually kind of crazy in thinking back on it, because it's kind of like there was this long period in civilization where people thought the ancients had it all figured out and will never figure out anything new.
Right.
And to some extent, that's the way I felt about physics when I was in the middle of doing it, so to speak, we've got quantum field theory. It's the foundation of what we're doing. And there's, yes, there's probably something underneath this, but we'll sort of never figure it out. But then I started studying simple programs in the computational universe, things like cellular automata and so on. And I discovered that they do all kinds of things that were completely at odds with the intuition that I had had. And so after that, after you see this tiny little program that does all this amazingly complicated stuff, then you start feeling a bit more ambitious about physics and saying, maybe we could do this for physics too. And so that got me started years ago now in this kind of idea of, could we actually find what's underneath all of these frameworks like quantum field theory and general relativity and so on. And people perhaps don't realize as clearly as they might that, the frameworks we're using for physics, which is basically these two things, quantum field theory, the theory of small stuff, and general relativity, theory of gravitation and large stuff. Those are the two basic theories, and they're 100 years old. I mean, general relativity was 1915, quantum field theory, 1920s. So basically 100 years old. And it's been a good run. There's a lot of stuff been figured out. But what's interesting is the foundations haven't changed in all that period of time, even though the foundations had changed several times before that, in the 200 years earlier than that. And I think the kinds of things that I'm thinking about, which are sort of really informed by thinking about computation and the computational universe, it's a different foundation. It's a different set of foundations, and might be wrong, but it is at least, we have a shot. And I think it's, to me, it's, my personal calculation for myself is if it turns out that finding the fundamental theory of physics, it's kind of low-hanging fruit, so to speak. Mm-hmm. It'd be a shame if we just didn't think to do it. If people just said, oh, you'll never figure that stuff out, let's, and it takes another 200 years before anybody gets around to doing it. I think it's, I don't know how low-hanging this fruit actually is. It may be, that it's kind of the wrong century to do this project. I mean, I think the cautionary tale for me, I think about things that I've tried to do in technology where people thought about doing them a lot earlier. I mean, my favorite example is probably Leibniz, who thought about essentially encapsulating the world's knowledge in a computational form in the late 1600s, and did a lot of things towards that. And basically, we finally managed to do this, but he was 300 years too early. Yeah. And that's kind of in terms of life planning, it's kind of like avoid things that can't be done in your century, so to speak.
Yeah, timing is everything. So you think if we kind of figure out the underlying rules it can create from which quantum field theory and general relativity can emerge, do you think that'll help us unify it at that level of abstraction?
Oh, we'll know it completely. We'll know how that all fits together. Yes, without a question. And it's already, even the things I've already done, they're very, it's very, very elegant, actually, how things seem to be fitting together. Now, is it right? I don't know yet. It's awfully suggestive. If it isn't right, it's then the designer of the universe should feel embarrassed, so to speak, because it's a really good way to do it.
And your intuition in terms of designing a universe, does God play dice? Is there randomness in this thing, or is it deterministic? So the kind of
That's a little bit of a complicated question, because when you're dealing with these things that involve these rewrites that have
even randomness is an emergent phenomenon, perhaps.
Yes. I mean, randomness in many of these systems, pseudo-randomness and randomness are hard to distinguish. In this particular case, the current idea that we have about measurement in quantum mechanics is something very bizarre and very abstract, and I don't think I can yet explain it without kind of yakking about very technical things. Eventually, I will be able to, but if that's right, it's kind of it's a weird thing, because it slices between determinism and randomness in a weird way that hasn't been sliced before, so to speak. So like many of these questions that come up in science, where it's like, is it this or is it that? Turns out the real answer is it's neither of those things. It's something kind of different and sort of orthogonal to those categories. And so that's the current, this week's idea about how that might work. But we'll see how that unfolds. I mean, there's this question about a field like physics and sort of the quest for a fundamental theory and so on. And there's both the science of what happens and there's the sort of the social aspect of what happens. Because, in a field that is basically as old as physics, we're at, I don't know what it is, fourth generation, I don't know, fifth generation, I don't know what generation it is of physicists. And like, I was one of these, so to speak. And for me, the foundations were like the pyramids, so to speak. It was that way, and it was always that way. It is difficult in an old field to go back to the foundations and think about rewriting them. It's a lot easier in young fields where you're still dealing with the first generation of people who invented the field. And it tends to be the case, that the nature of what happens in science tends to be, you'll get, typically the pattern is some methodological advance occurs. And then there's a period of 5 years, 10 years, maybe a little bit longer than that, where there's lots of things that are now made possible by that methodological advance, whether it's, telescopes, or whether that's some mathematical method or something. It's, there's something happens, a tool gets built, and then you can do a bunch of stuff. And there's a bunch of low-hanging fruit to be picked. And that takes a certain amount of time. After that, all that low-hanging fruit is picked, then it's a hard slog for the next however many decades or century or more to get to the next sort of level at which one can do something. And it's kind of and it tends to be the case that in fields that are in that kind of, I wouldn't say cruise mode because it's really hard work, but it's very hard work for very incremental progress.
And then in your career and some of the things you've taken on, it feels like you haven't been afraid of the hard slog.
Yeah, that's true.
So it's quite interesting, especially on the engineering side. On a small tangent, when you were at Caltech, did you get to interact with Richard Feynman at all? Do you have any memories of Richard?
We worked together quite a bit, actually. In fact, both when I was at Caltech and after I left Caltech, we were both consultants at this company called Thinking Machines Corporation, which was just down the street from here, actually. Mm-hmm. As ultimately ill-fated company, but I used to say this company is not going to work with the strategy they have, and Dick Feynman always used to say, "What do we know about running companies? Just let them run their company." But anyway, he was not into that kind of thing, and he always thought that my interest in doing things like running companies was a distraction, so to speak. For me, it's a mechanism to have a more effective machine for actually figuring things out and getting things to happen.
Did he think of it, because essentially what you did with the company, I don't know if you were thinking of it that way, but you're creating tools to empower the exploration of the universe. Do you think, did he
understand that point?
The point of tools of...
I think not as well as he might have done. I mean, I think that, but, he was actually my first company, which was also involved with more mathematical computation kinds of things. he was he had lots of advice about the technical side of what we should do and so on.
Do you have examples, memories, of thoughts that?
Oh yeah. He had all kinds of in the business of doing sort of one of the hard things in math is doing integrals and so on, right? Mm-hmm. And so he had his own elaborate ways to do integrals and so on. He had his own ways of thinking about sort of getting intuition about how math works. And so his sort of meta idea was take those intuitional methods and make a computer follow those intuitional methods. Now, it turns out, for the most part, like when we do integrals and things, what we do is we build this kind of bizarre industrial machine that turns every integral into, products of Mayer G functions and generates this very elaborate thing. And actually, the big problem is turning the results into something a human will understand. It's not, quotes, doing the integral. And actually, Feynman did understand that to some extent. And I'm embarrassed to say he once gave me this big pile of, calculational methods for particle physics that he worked out in the 50s. And he said, it's more use to you than to me type thing. And I was like, I intended to look at it and give it back, and I'm still in my files now. So it's, but that's what happens when it's finiteness of human lives. Maybe if he'd lived another 20 years, I would have remembered to give it back. But I think it's, that was his attempt to systematize the ways that one does integrals that show up in particle physics and so on. Turns out the way we've actually done it is very different from that way.
What do you make of that difference between, so Feynman was actually quite remarkable at creating sort of intuitive, like diving in, creating intuitive frameworks for understanding difficult concepts.
I'm smiling because, the funny thing about him was that the thing he was really, really, really good at is calculating stuff. But he thought that was easy because he was really good at it. And so he would do these things where he would calculate do some complicated calculation in quantum field theory, for example, come out with a result. Wouldn't tell anybody about the complicated calculation because he thought that was easy. He thought the really impressive thing was to have this simple intuition about how everything works. So he invented that at the end. Mm-hmm. And, because he'd done this calculation and knew how it worked, it was a lot easier. It's a lot easier to have good intuition when you know what the answer is. and then he would just not tell anybody about these calculations. Yeah. And he wasn't meaning that maliciously, so to speak. It's just he thought that was easy. Yeah. And that's, that led to areas where people were just completely mystified and they kind of followed his intuition, but nobody could tell why it worked. Because actually the reason it worked was because he'd done all these calculations and he knew that it would work. And, when he and I worked a bit on quantum computers, actually back in 1980, 81, before anybody had heard of those things. And, the typical mode of, he always used to say, and I now think about this because I'm about the age that he was when I worked with him. And, I see the people who are 1/3 my age, so to speak. Mm-hmm. And he was always complaining that I was 1/3 his age and therefore various things. But he would do some calculation by hand, on a blackboard and things, come up with some answer. I'd say, I don't understand this. I do something with a computer and he'd say, I don't understand this. So there'd be some big argument about what was going on, but it was always and I think actually many of the things that we sort of realized about quantum computing that were sort of issues that have to do particularly with the measurement process are kind of still issues today. And I kind of find it interesting. It's a funny thing in science that these, there's a remarkable, it happens in technology too, there's a remarkable sort of repetition of history that ends up occurring. Eventually things really get nailed down, but it often takes a while and things come back decades later. For example, I could tell a story actually happened right down the street from here. When we were both at Thinking Machines, I had been working on this particular cellular automaton called Rule 30 that has this feature that from very simple initial conditions, it makes really complicated behavior. Okay. So, and actually of all silly physical things, using this big parallel computer called a connection machine that company was making, I generated this giant printout of Rule 30 on the same kind of printer that people use to make layouts for microprocessors. So one of these big large format printers with high resolution and so on. So print this out, lots of very tiny cells. And so there was sort of a question of how some features of that pattern. And so it was very much a physical, on the floor with meter rules trying to measure different things. Mm-hmm. So Feynman kind of takes me aside. We've been doing that for a little while, and takes me aside and he says, I just want to know this one thing. He says, I want to know, how did you know that this Rule 30 thing would produce all this really complicated behavior that is so complicated that we're, going around with this big printout and so on? And I said, well, I didn't know. I just enumerated all the possible rules and then observed that that's what happened. He said, I feel a lot better. I thought you had some intuition that he didn't have that would let one. I said, no intuition, just experimental science.
Oh, that's such a beautiful sort of dichotomy there. Of that's exactly what you showed, is you really can't have an intuition about an irreducible. I mean, you have to run it.
Yes, that's right.
That's so hard for us humans, and especially brilliant physicists like Feynman, to say that you can't have a compressed, clean intuition about how the whole thing works.
Yes. No, I think he was sort of on the edge of understanding that point about computation. And I think he found that. I think he always found computation interesting, and I think that was sort of what he was a little bit poking at. That intuition, the difficulty of discovering things, like even you say, you just enumerate all the cases and you just find one that does something interesting, right? Sounds very easy. Turns out, like, I missed it when I first saw it because I had kind of an intuition that said it shouldn't be there. Mm-hmm. So I had kind of arguments, I'm going to ignore that case because whatever.
How did you have an open mind enough? Because you're essentially the same person as Richard Feynman, like the same kind of physics type of thinking. How did you find yourself having a sufficiently open mind to be open to watching rules and them revealing complexity?
Yeah, I think that's an interesting question. I've wondered about that myself, because it's kind of like, you live through these things and then you say, what was the historical story? And sometimes the historical story that you realize after the fact was not what you lived through, so to speak. And so what I realized is, I think what happened is, I did physics kind of like reductionistic physics, where you're thrown the universe and you're told, go figure out what's going on inside it. And then I started building computer tools, and I started building my first computer language, for example. And computer language is not like, it's sort of like physics in the sense that you have to take all those computations people want to do and kind of drill down and find the primitives that they can all be made of. But then you do something that's really different, because you're just saying, okay, these are the primitives. Now, hopefully they'll be useful to people. Let's build up from there. So you're essentially building an artificial universe in a sense, where you make this language, you've got these primitives, you're just building whatever you feel like building. Mm-hmm. And so it was sort of interesting for me, because from doing science where you're just thrown the universe as the universe is, to then just being told, you can make up any universe you want. And so I think that experience of making a computer language, which is essentially building your own universe, so to speak, is, that's kind of the, that's what gave me a somewhat different attitude towards what might be possible. It's like, let's just explore what can be done in these artificial universes, rather than thinking the natural science way of let's be constrained by how the universe actually is.
Yeah, by being able to program, essentially you've, as opposed to being limited to just your mind and a pen, you've basically built another brain that you can use to explore the universe by a computer program, is a kind of a brain.
Right. And it's or a telescope, or, it's a tool.
Yeah,
it lets you see stuff.
But there's something fundamentally different between a computer and a telescope. I mean, I'm hoping not to romanticize the notion, but it's more general. The computer is more general than a telescope.
And it's I think, this point about, people say, such and such a thing was almost discovered at such and such a time. The distance between, the building the paradigm that allows you to actually understand stuff, or allows one to be open to seeing what's going on, that's really hard. And, I think I've been fortunate in my life that I've spent a lot of my time building computational language, and that's an activity that, in a sense, works by sort of having to kind of create another level of abstraction and kind of be open to different kinds of structures. But it's always. I mean, I'm fully aware of, I suppose, the fact that I have seen it a bunch of times of how easy it is to miss the obvious, so to speak. That at least is factored into my attempt to not miss the obvious, although it may not succeed.
What do you think is the role of ego in the history of math and science? And more sort of, a book title is something like A New Kind of Science. You've accomplished a huge amount. And in fact, somebody said that Newton didn't have an ego, and I looked into it and he had a huge ego. Yeah. But from an outsider's perspective, some have said that you have a bit of an ego as well. Do you see it that way? Does ego get in the way? Is it empowering? Is it both
it's complicated and necessary. I mean, I've spent more than half my life CEOing a tech company.
Right.
Okay. And, that is I think it's actually very, it means that one's ego is not a distant thing. It's a thing that one encounters every day, so to speak, because it's all tied up with leadership and with how one, develops an organization and all these kinds of things. So, it may be that if I'd been an academic, for example, I could have sort of, checked the ego, put it on a shelf somewhere and ignored its characteristics. But
you're reminded of it quite often in the context of running a company.
Sure. Yeah. I mean, that's what it's about. It's about leadership, and leadership is intimately tied to ego. Now, what does it mean? I mean, what is the, for me, I've been fortunate that I think I have reasonable intellectual confidence, so to speak. Mm-hmm. That is, I'm one of these people who at this point, if somebody tells me something and I just don't understand it, my conclusion isn't that means I'm dumb. My conclusion is there's something wrong with what I'm being told. And that was actually Dick Feynman used to have that feature too. He never really believed in. He actually believed in experts much less than I believe in experts. So.
Wow. So that's a fundamentally powerful property of ego, and saying like, not that I am wrong, but that the world is wrong, and telling me, like, when confronted with a fact that doesn't fit the thing that you've really thought through, sort of both the negative and the positive of ego. Yeah. Do you see the negative of that get in the way? Sort of being confronted.
There are mistakes I've made that are the result of I'm pretty sure I'm right, and turns out I'm not. I mean, that's the, but the thing is that the idea that one tries to do things that, so for example, one question is, if people have tried hard to do something and then one thinks maybe I should try doing this myself, if one does not have a certain degree of intellectual confidence, one just says, well, people have been trying to do this for 100 years. Yeah. How am I going to be able to do this?
Yeah.
And, I was fortunate in the sense that I happened to start having some degree of success in science and things when I was really young. And so that developed a certain amount of sort of intellectual confidence that I don't think I otherwise would have had. Yeah. And, in a sense, I mean, I was fortunate that I was working in a field, particle physics, during its sort of golden age of rapid progress. And that's kind of gives one a false sense of achievement, because it's kind of easy to discover stuff that's going to survive if you happen to be, picking the low-hanging fruit of a rapidly expanding field.
I mean, the reason I totally immediately understood the ego behind A New Kind of Science, to me, let me sort of just try to express my feelings on the whole thing, is that if you don't allow that kind of ego, then you would never write that book. That you would say, well, people must have done this. You would not dig. You would not keep digging. Right. And I think you have to take that ego and ride it and see where it takes you. And that's how you create exceptional work.
But I think the other point about that book was it was a non-trivial question, how to take a bunch of ideas that are, I think, reasonably big ideas. They might, their importance is determined by what happens historically. One can't tell how important they are. One can tell sort of the scope of them. And the scope is fairly big. And they're very different from things that have come before. And the question is, how do you explain that stuff to people? And so I had the experience of sort of saying, well, there are these things, there's a cellular automaton, it does this, it does that. And people are like, oh, it must be just like this. It must be just like that. I said, no, it isn't. It's something different, right?
And so you could have done sort of, I'm really glad you did what you did, but you could have done sort of academically, just keep publishing small papers here and there. And then you would just keep getting this kind of resistance, right? You would get like,
yes,
it's supposed to just dropping a thing that says, here it is.
Yeah,
here's
right.
the full thing.
Right. No, I mean, that was my calculation, is that basically, you could introduce little pieces. It's like, one possibility is like, it's the secret weapon, so to speak. It's this, I keep on, discovering these things in all these different areas. Where did they come from? Nobody knows. But I decided that, in the interests of one only has one life to lead, and, writing that book took me a decade anyway. There's not a lot of wiggle room, so to speak. One can't be wrong by a factor of 3, so to speak, in how long it's going to take. That I thought the best thing to do, the thing that is most sort of that most respects the intellectual content, so to speak, is you just put it out with as much force as you can, because it's not something where, and it's an interesting thing. You talk about ego, and it's for example, I run a company which has my name on it, right? I thought about starting a club for people whose companies have their names on them, and it's a funny group, because we're not a bunch of egomaniacs. That's not what it's about, so to speak. It's about basically sort of taking responsibility for what one's doing, and in a sense, any of these things where you're sort of putting yourself on the line, it's kind of a funny it's a funny dynamic, because in a sense, my company is sort of something that happens to have my name on it, but it's kind of bigger than me, and I'm kind of just its mascot at some level. I also happen to be a pretty strong leader of it, but
it's basically showing a deep, inextricable sort of investment. The same, your name, like Steve Jobs' name wasn't on Apple, but he was Apple.
Yes.
Elon Musk's name is not on Tesla, but he is Tesla. So it's like, meaning emotionally. If a company succeeds or fails, he would that emotionally would suffer through that.
Yes.
And so that's a beautiful
recognizing that fact,
and also Wolfram is a pretty good branding name, so it works out.
Yeah, right, exactly. I think Steve had a bad deal there.
Yeah. So you made up for it with the last name. Okay, so in 2002 you published A New Kind of Science, to which, sort of on a personal level, I can credit my love for cellular automata and computation in general. I think a lot of others can as well. Can you briefly describe the vision, the hope, the main idea presented in this 1,200-page book?
Sure. Although it took 1,200 pages to say in the book. So no, the real idea, it's kind of a good way to get into it, is to look at sort of the arc of history and to look at what's happened in kind of the development of science. I mean, there was this sort of big idea in science about 300 years ago that was, let's use mathematical equations to try and describe things in the world. Let's use sort of the formal idea of mathematical equations to describe what might be happening in the world, rather than, for example, just using sort of logical augmentation and so on. Let's have a formal theory about that. And so there'd been this 300-year run of using mathematical equations to describe the natural world, which had worked pretty well. But I got interested in how one could generalize that notion. There is a formal theory, there are definite rules, but what structure could those rules have? And so what I got interested in was, let's generalize beyond the sort of purely mathematical rules, and we now have this sort of notion of programming and computing and so on. Let's use the kinds of rules that can be embodied in programs as a sort of generalization of the ones that can exist in mathematics, as a way to describe the world. And so my kind of favorite version of these kinds of simple rules are these things called cellular automata. And so typical case.
So wait, what are cellular automata?
Fair enough. So typical case of a cellular automaton, it's an array of cells. It's just a line of discrete cells. Each cell is either black or white. And in a series of steps that you can represent as lines going down a page, you're updating the color of each cell according to a rule that depends on the color of the cell above it and to its left and right. So it's really simple. So a thing might be, if the cell and its right neighbor are not the same, and or the cell on the left is black or something, then make it black on the next step, and if not, make it white. Typical rule. That rule, I'm not sure I said it exactly right, but a rule very much like what I just said, has the feature that if you started off from just one black cell at the top, it makes this extremely complicated pattern. So some rules, you get a very simple pattern. Some rules, you have the rule is simple, you start them off from a sort of simple seed, you just get this very simple pattern. But other rules, and this was the big surprise when I started actually just doing the simple computer experiments to find out what happens, is that they produce very complicated patterns of behavior. So for example, this Rule 30 rule has the feature you started off from just one black cell at the top, makes this very random pattern. If you look like at the center column of cells, you get a series of values, it goes black, white, black, black, whatever it is. That sequence seems for all practical purposes random. So it's kind of like in math, you compute the digits of pi, 3.1415926, whatever. Those digits, once computed, the scheme for computing pi, it's the ratio of the circumference to diameter of a circle, very well defined, but yet when you are once you've generated those digits, they seem for all practical purposes completely random. And so it is with Rule 30, that even though the rule is very simple, much simpler, much more sort of computationally obvious than the rule for generating the digits of pi, even with a rule that simple, you're still generating immensely complicated behavior.
Yeah, so if we could just pause on that. I think you probably said it and looked at it so long, you forgot the magic of it. Or perhaps you don't, you still feel the magic, but to me, if you've never seen sort of, I would say, what is it? A one-dimensional, essentially, cellular automata, right? And you were to guess what you would see if you have some sort of cells that only respond to its neighbors.
Right.
If you were to guess what kind of things you would see, like my initial guess, like even when I first opened your book, A New Kind of Science, right? My initial guess is you would see, it would be very simple stuff.
Right.
And I think it's a magical experience to realize the kind of complexity. You mentioned Rule 30. Still your favorite cellular automaton?
Still my favorite rule, yes.
You get complexity, immense complexity. You get arbitrary complexity.
Yes.
And when you say randomness down the middle column, that's just one a cool way to say that there's incredible complexity. And that's that's a magical idea. However you start to interpret it, all the reducibility discussions, all that, but it's just, I think that has profound philosophical kind of notions around it too. It's not just, it's transformational about how you see the world. I think for me, it was transformational. I don't know, we can have all kinds of discussions about computation and so on, but just, I sometimes think if I were on a desert island and was, I don't know, maybe it was some psychedelics or something, but if I had to take one book, New Kind of Science would be it, because you can just enjoy that notion. For some reason, it's a deeply profound notion, at least to me.
I find it that way. Yeah. Look, it was a very intuition-breaking thing to discover. It's kind of like, you point the computational telescope out there and suddenly you see, I don't know, in the past, it's kind of like, moons of Jupiter or something, but suddenly you see something that's kind of very unexpected. And Rule 30 was very unexpected for me. And the big challenge at a personal level was to not ignore it. People, in other words, you might say,
it's a bug. What would you say? Yeah. What would you
say?
What are we looking at, by the way?
Well, I was just generating here. I'll actually generate a Rule 30 pattern. So that's the rule for Rule 30. And it says, for example, here, if you have a black cell in the middle and a black cell to the left and a white cell to the right, then the cell on the next step will be white. And so here's the actual pattern that you get starting off from a single black cell at the top there. Then
that's the initial state, initial condition.
That's the initial thing. You just start off from that, and then you're going down the page. And at every step, you're just applying this rule to find out the new value that you get. And so you might think, rule that simple, you got to get there's got to be some trace of that simplicity here. Okay, we'll run it, let's say, for 400 steps. That's what it does. It's kind of aliasing a bit on the screen there, but you can see there's a little bit of regularity over on the left, but there's a lot of stuff here that just looks very complicated, very random, and that's a big sort of was a big shock to my intuition, at least, that's possible.
The mind immediately starts, is there a pattern? There must be a repetitive pattern.
Yeah,
there must be. That's where the mind goes.
So indeed, that's what I thought at first. And I thought, well, this is kind of interesting, but, if we run it long enough, we'll see, something will resolve into something simple. And, I did all kinds of analysis of using mathematics, statistics, cryptography, whatever, to try and crack it. And I never succeeded. And after I hadn't succeeded for a while, I started thinking maybe there's a real phenomenon here that is the reason I'm not succeeding. Maybe, the thing that for me was sort of a motivating factor was looking at the natural world and seeing all this complexity that exists in the natural world. The question is, where does it come from? What secret does nature have that lets it make all this complexity that we humans, when we engineer things, typically are not making? We're typically making things that at least look quite simple to us. And so the shock here was, even from something very simple, you're making something that complex. Maybe this is getting at sort of the secret that nature has that allows it to make really complex things, even though its underlying rules may not be that complex.
How did it make you feel? If we look at the Newton apple, was there you took a walk and something, it profoundly hit you, or was this a gradual thing? A lobster being boiled?
The truth of every sort of science discovery is it's not that gradual. I happen to be interested in scientific biography kinds of things. And so I've tried to track down, how did people come to figure out this or that thing? And there's always a long kind of sort of preparatory, there's a need to be prepared in a mindset in which it's possible to see something. In the case of Rule 30, I don't know, it was around June 1st, 1984, was kind of a silly story in some ways. I finally had a high-resolution laser printer. So I thought, I'm going to generate a bunch of pictures of these cellular automata. And I generate this one, and I was on some plane flight to Europe, and I have this with me. And it's like, I really should try to understand this. And this is really, I really don't understand what's going on. And that was kind of the, slowly trying to see what was happening. It was depressingly unsudden, so to speak, in the sense that a lot of these ideas, like principle of computational equivalence, for example, I thought, well, that's a possible thing. I didn't know if it's correct. Still don't know for sure that it's correct. But it's sort of a gradual thing that these things gradually kind of seem more important than one thought. I think the whole idea of studying the computational universe of simple programs, it took me probably a decade and a half to kind of internalize that was really an important idea. And I think, if it turns out we find the whole universe lurking out there in the computational universe, that's a good, it's a good brownie point or something for the whole idea. But I think that the thing that's strange in this whole question about, finding this different raw material for making models of things, what's been interesting sort of in the sort of arc of history is, for 300 years, it's kind of like the mathematical equations approach. It was the winner. It was the thing, you want to have a really good model for something, that's what you use. The thing that's been remarkable is just in the last decade or so, I think one can see a transition to using not mathematical equations, but programs as sort of the raw material for making models of stuff. Mm-hmm. And that's pretty neat. And it's kind of, as somebody who's kind of lived inside this paradigm shift, so to speak, it is bizarre. No doubt in sort of the history of science, that will be seen as an instantaneous paradigm shift. But it sure isn't instantaneous when it's played out in one's actual life, so to speak.
Right.
It seems glacial, and it's the kind of thing where it's sort of interesting because in the dynamics of sort of the adoption of ideas like that into different fields, the younger the field, the faster the adoption typically, because people are not kind of locked in with the fifth generation of people who've studied this field, and it is the way it is, and it can never be any different. And I think that's been, watching that process has been interesting. I mean, I think I'm fortunate that I do stuff mainly because I like doing it, and if I was that makes me kind of thick-skinned about the world's response to what I do. But that's definitely, and any time you write a book called something like A New Kind of Science, it's kind of the pitchforks will come out for the old kind of science. And it was interesting dynamics. I think that I have to say that I was fully aware of the fact that when you see sort of incipient paradigm shifts in science, the vigor of the negative response upon early introduction is a fantastic positive indicator of good long-term results. So in other words, if people just don't care, it's, that's not such a good sign. If they're like, oh, this is great, that means you didn't really discover anything interesting.
What fascinating properties of Rule 30 have you discovered over the years? You've recently announced the Rule 30 prizes for solving 3 key problems. Can you maybe talk about interesting properties that have been kind of revealed, Rule 30 or other cellular automata, and what problems are still before us, like the 3 problems you've announced?
Yeah, right. So, I mean, the most interesting thing about cellular automata is that it's hard to figure stuff out about them. And that's, in a sense, every time you try and sort of, you try and bash them with some other technique, you say, can I crack them? The answer is they seem to be uncrackable. They seem to have the feature that they are, that they're sort of showing irreducible computation. You're not able to say, oh, I know exactly what this is going to do. It's going to do this or that.
But there's specific formulations of that fact.
Yes, right. So, I mean, for example, in Rule 30, in the pattern you get just starting from a single black cell, you get this sort of very, very sort of random looking pattern. And so one feature of that, just look at the center column. And for example, we used that for a long time to generate randomness in Wolfram Language, what Rule 30 produces. Now, the question is, can you prove how random it is? So, for example, one very simple question, can you prove that it'll never repeat? No, we haven't been able to show that it will never repeat. We know that if there are 2 adjacent columns, we know they can't both repeat. But just knowing whether that center column can ever repeat, we still don't even know that. Another problem that I sort of put in my collection of, it's like $30,000 for 3, for these 3 prizes for about Rule 30. I would say that this is not one of those. This is one of those cases where the money is not the main point, but it's just helps motivate somehow the investigation.
So there's 3 problems you propose. You get $30,000 if you solve all 3, or maybe I don't know.
No, it's $10,000 for each.
For each, right?
Yeah.
The problems. That's right. Money is not the thing. The problems themselves are just clean,
right.
formulations.
So it's just will it ever become periodic? Second problem is, are there an equal number of black and white cells?
Down the middle column. And the third problem is a little bit harder to state, which is essentially, is there a way of figuring out what the color of a cell at position T down the center column is with a less computational effort than about T steps? So in other words, is there a way to jump ahead and say, I know what this is going to do. It's just some mathematical function of T. Or proving that there is no way.
Or proving there is no way, yes. But both, for any one of these, one could prove that, one could discover, we know what Rule 30 does for 1 billion steps, but, and maybe we'll know for 1 trillion steps before too very long. But maybe at 1 quadrillion steps, it suddenly becomes repetitive. You might say, how could that possibly happen? But so when I was writing up these prizes, I thought, and this is typical of what happens in the computational universe, I thought, let me find an example where it looks like it's just going to be random forever, but actually it becomes repetitive.
Yeah.
And I found one. And it's just, I did a search. I searched, I don't know, maybe 1 million different rules with some criterion. And this is, what's sort of interesting about that is I kind of have this thing that I say in a kind of silly way about the computational universe, which is, the animals are always smarter than you are. That is, there's always some way one of these computational systems is going to figure out how to do something, even though I can't imagine how it's going to do it. And, I didn't think I would find one that, you would think after all these years that when I found sort of all possible things, funky things, that I would have gotten my intuition wrapped around the idea that, these creatures are always in the computational universe are always smarter than I'm going to be. But,
well, they're equivalently as smart, right?
That's correct. and that makes one feel very sort of, it's humbling every time, because every time the thing is you think it's going to do this, or it's not going to be possible to do this. And it turns out it finds a way.
Of course, the promising thing is there's a lot of other rules like Rule 30. It's just Rule 30 is...
Oh, it's my favorite because I found it first. And
that's right. But the problems are focusing on Rule 30. It's possible that Rule 30 is repetitive after a trillion steps.
It is possible.
And that doesn't prove anything about the other rules.
It does not.
But this is a good sort of experiment of how you go about trying to prove something about a particular rule.
Yes. And it also, all these things help build intuition. That is, if it turned out that this was repetitive after a trillion steps, that's not what I would expect. And so we learn something from that.
The method to do that, though, would reveal something interesting about the cellular automata stuff.
No doubt. I mean, it's although it's sometimes challenging. Like I put out a prize in 2007 for a particular Turing machine that was the simplest candidate for being a universal Turing machine, and the young chap in England named Alex Smith, after a smallish number of months, said, "I've got a proof." And he did. It took a little while to iterate, but he had a proof. Unfortunately, the proof is it's a lot of micro details. It's not like you look at it and you say, aha, there's a big new principle. The big new principle is the simplest Turing machine that might have been universal actually is universal. And it's incredibly much simpler than the Turing machines that people already knew were universal before that. And so that intuitionally is important because it says, computational universality is closer at hand than you might have thought. But the actual methods are not, in that particular case, were not terribly illuminating.
Yeah, it would be nice if the methods would also be elegant.
That's true. Yeah, no, I mean, I think it's one of these things where, it's like a lot of, we've talked about earlier, kind of, opening up AIs and machine learning and things of what's going on inside. Yeah. And is it just step by step, or can you sort of see the bigger picture more abstractly?
It's unfortunate. With Fermat's last theorem proof, it's unfortunate that the proof to such an elegant theorem is not. It's not. It doesn't fit into the margins of a page.
That's true. But one of the things is that's another consequence of computational irreducibility. This fact that there are even quite short results in mathematics whose proofs are arbitrarily long. Yes, that's a consequence of all this stuff, and it makes one wonder. How come mathematics is possible at all?
Right.
Why is it the case? How have people managed to navigate doing mathematics through looking at things where they're not just thrown into it's all undecidable? That's its own separate story.
And that would have a poetic beauty to it if people were to find something interesting about Rule 30, because there's an emphasis to this particular rule. It wouldn't say anything about the broad irreducibility of all computations, but it would nevertheless put a few smiles on people's faces of...
But to me, it's like, in a sense, establishing the principle of computational equivalence, it's a little bit like doing inductive science anywhere. That is, the more examples you find, the more convinced you are that it's generally true. We don't get to, whenever we do natural science, we say, well, it's true here, that this or that happens. Can we prove that it's true everywhere in the universe? No, we can't. So, it's the same thing here. We're exploring the computational universe. We're establishing facts in the computational universe, and that's sort of a way of inductively concluding general things.
Just to think through this a little bit, we've touched on it a little bit before, but what's the difference between the kind of computation, now that we've talked about cellular automata, what's the difference between the kind of computation, biological systems, our mind, our bodies, the things we see before us that emerge through the process of evolution, and cellular automata? We've kind of implied through the discussion of physics underlying everything, but we talked about the potential equivalence of the fundamental laws of physics and the kind of computation going on in Turing machines. But can you now connect that? Do you think there's something special or interesting about the kind of computation that our bodies do?
Right. Well, let's talk about brains primarily.
Brains.
I think the most important thing about the things that our brains do are that we care about them, in the sense that there's a lot of computation going on out there,
right,
in cellular automata and physical systems and so on, and it does what it does. It follows those rules. It does what it does. The thing that's special about the computation in our brains is that it's connected to our goals and our kind of whole societal story, and I think that's the special feature. And now the question then is, when you see this whole sort of ocean of computation out there, how do you connect that to the things that we humans care about? Mm-hmm. And in a sense, a large part of my life has been involved in sort of the technology of how to do that. And, what I've been interested in is kind of building computational language that allows that something that both we humans can understand and that can be used to determine computations that are actually computations we care about. See, I think when you look at something like one of these cellular automata and it does some complicated thing, you say, that's fun, but why do I care? Well, you could say the same thing actually in physics. You say, oh, I've got this material and it's a ferrite or something. Why do I care? It has some magnetic properties. Why do I care? It's amusing, but why do I care? Well, we end up caring because, ferrite is what's used to make magnetic tape, magnetic disks, whatever. Or, we could use liquid crystals used to make, not actually, increasingly not, but it has been used to make computer displays and so on. But so in a sense, we're mining these things that happen to exist in the physical universe and making it be something that we care about because we sort of entrain it into technology. Mm-hmm. And it's the same thing in the computational universe, that a lot of what's out there is stuff that's just happening, but sometimes we have some objective and we will go and sort of mine the computational universe for something that's useful for some particular objective. On a large scale, trying to do that, trying to sort of navigate the computational universe to do useful things, that's where computational language comes in. And, a lot of what I've spent time doing and building this thing we call Wolfram Language, which I've been building for the last 1/3 of a century now. The goal there is to have a way to express kind of computational thinking, computational thoughts in a way that both humans and machines can understand. So it's kind of like in the tradition of computer languages, programming languages, that the tradition there has been more, let's take how computers are built and let's have a human way to specify, do this, do this, do this at the level of the way that computers are built. What I've been interested in is representing sort of the whole world computationally and being able to talk about whether it's about cities or chemicals or, this kind of algorithm or that kind of algorithm, things that have come to exist in our civilization and the sort of knowledge base of our civilization, being able to talk directly about those in a computational language so that both we can understand it and computers can understand it. I mean, the thing that I've been sort of excited about recently, which I had only realized recently, which is kind of embarrassing, but is kind of the arc of what we've tried to do in building this kind of computational language is it's a similar kind of arc of what happened when mathematical notation was invented. Mm-hmm. So go back 400 years, people were trying to do math. They were always explaining their math in words. And it was pretty clunky. And as soon as mathematical notation was invented, you could start defining things like algebra and later calculus and so on. It all became much more streamlined. When we deal with computational thinking about the world, there's a question of what is the notation? What is the kind of formalism that we can use to talk about the world computationally? And in a sense, that's what I've spent the last third of a century trying to build. And we finally got to the point where we have a pretty full-scale computational language that sort of talks about the world. And that's exciting because it means that just like having this mathematical notation let us talk about the world mathematically, we now and let us build up these kind of mathematical sciences. Now we have a computational language which allows us to start talking about the world computationally and lets us, my view of it is it's kind of computational X for all X, all these different fields of, computational this, computational that. That's what we can now build.
Let's step back. So first of all, the mundane. What is Wolfram Language in terms of I can answer the question for you, but it's basically not the philosophical, deep, the profound, the impact of it. I'm talking about in terms of tools, in terms of things you can download, in terms of stuff you can play with. What is it? Where does it fit into the infrastructure? What are the different ways to interact with it?
Right. So, the two big things that people have sort of perhaps heard of that come from Wolfram Language, one is Mathematica, the other is Wolfram Alpha. So Mathematica first came out in 1988. It's this system that is basically an instance of Wolfram Language, and it's used to do computations, particularly in sort of technical areas. And the typical thing you're doing is you're typing little pieces of computational language, and you're getting computations done.
It's very kind of there's like a symbolic.
Yeah, it's a symbolic language. So
it's a symbolic language. So, I don't know how to cleanly express that, but that makes it very distinct from how we think about sort of, programming in a language like Python or something.
Right. So the point is that in a traditional programming language, the raw material of the programming language is just stuff that computers intrinsically do. And the point of Wolfram Language is that what the language is talking about is things that exist in the world or things that we can imagine and construct. It's aimed to be an abstract language from the beginning. Yeah. And so, for example, one feature it has is that it's a symbolic language, which means that, the thing called, you have an X, you just type in X, and Wolfram Language would just say, oh, that's X. It won't say error, undefined thing. I don't know what it is, computation, in terms of the internals of the computer. Now that X could perfectly well be, the city of Boston. That's a thing. That's a symbolic thing. Or it could perfectly well be the trajectory of some spacecraft represented as a symbolic thing. And that idea that one can work with, sort of computationally work with these kinds of things that exist in the world or describe the world, that's really powerful. And that's what, when I started designing, when I designed the predecessor of what's now Wolfram Language, which is a thing called SMP, which was my first computer language, I kind of wanted to have this sort of infrastructure for computation, which was as fundamental as possible. This is what I got for having been a physicist and tried to find, fundamental components of things, and wound up with this kind of idea of transformation rules for symbolic expressions as being sort of the underlying stuff from which computation would be built. And that's what we've been building from in Wolfram Language. And, operationally, what happens, it's, I would say, by far the highest level computer language that exists. And it's really been built in a very different direction from other languages. So other languages have been about, there is a core language. It really is kind of wrapped around the operations that a computer intrinsically does. Maybe people add libraries for this or that, but the goal of Wolfram Language is to have the language itself be able to cover this sort of very broad range of things that show up in the world. And that means that, there are 6,000 primitive functions in the Wolfram Language that cover things. I could probably pick a random here. I'm going to pick, just because, just for fun, I'll pick, let's take a random sample of all the things that we have here. So let's just say random sample of 10 of them, and let's see what we get. Wow, okay. So these are really different things from
these are all functions.
These are all functions. Boolean convert. Okay, that's a thing for converting between different types of Boolean expressions.
So for people just listening, Stephen typed in random sample of names. So this is sampling from all functions. How many you said there might be?
6,000.
6,000. From 6,000, 10 of them, and there's a hilarious variety of them.
Yeah, right. Well, we've got things about dollar requester address that has to do with interacting with the world of the cloud and so on. Discrete wavelet data, spheroidal.
It's also graphical sort of window movable.
Yeah, window movable. That's a user interface kind of thing. I want to pick another 10 because I think this is okay. So yeah, there's a lot of infrastructure stuff here that you see if you just start sampling at random. There's a lot of kind of infrastructural things. If you more look at the
some of the exciting machine learning stuff you showed off, is that also in this pool?
Oh yeah. I mean, so one of those functions is like image identify as a function here. We can just say image identify. I don't know. It's always good to. Let's do this. Let's say current image, and let's pick up an image. Hopefully.
Typed in a current image, accessing the webcam, took a picture of yourself.
Took a terrible picture, but anyway, we can say image identify, open square brackets, and then we just paste that picture in there.
So image identify function running on the picture that you just took.
Says, oh wow, it says I look like a plunger because I got this great big thing behind my
classify. So this image identify classifies the most likely object in the image, right. And it so it was a plunger.
Okay, that's a bit embarrassing. Let's see what it does. Let's pick the top 10. Okay. Well, it thinks it's pretty unlikely that it's a primate, a hominid, a person.
8% probability.
Yeah, that's
57 is a plunger.
Yeah, well,
hopefully will not give you an existential crisis. And then 8%, or no, I shouldn't say percent, but
no, that's right. 8% that it's a hominid. Okay, it's really. I'm going to do another one of these just because I'm embarrassed that it. Oops, no, it didn't even see me at all. There we go. Let's try that. Let's see what that did.
Retook a picture with
right,
a little bit more
with
of
me,
your
a little bit more of me, and not just my bald head, so to speak. Okay, 89% probability it's a person. So then I would. So this is image identify as an example of one
just one of them,
just one function out of 6,000.
And that's part of the. That's part of the language.
Core language, yes. And I mean, something like I could say, I don't know. Let's find the geo-nearest. What could we find? Let's find the nearest volcano. Let's find the 10. I wonder where it thinks here is. Let's try finding the 10 volcanoes nearest here. Okay.
So geo nearest volcano here, 10 nearest volcanoes.
Right. Let's find out where those are. We got a list of volcanoes out, and I can say geo list plot that. And hopefully, okay, so there we go. So there's a map that shows the positions of those 10 volcanoes.
Of the East Coast and the Midwest. And well, no, we're okay. We're okay. It's not too bad.
Yeah, they're not very close to us. We could measure how far away they are. But, the fact that right in the language, it knows about all the volcanoes in the world. It knows, computing what the nearest ones are. It knows all the maps of the world and so on.
It's a fundamentally different idea of what a language is.
Yeah, right. That's why I like to talk about it as a full-scale computational language. That's what we've tried to do.
And just if you can comment briefly, I mean, this kind of the Wolfram language, along with Wolfram Alpha, represents kind of what the dream of what AI is supposed to be. There's now a sort of a craze of learning kind of idea that we can take raw data and from that extract the different hierarchies of abstractions, and in order to be able to in order to form the kind of things that Wolfram language operates with. But we're very far from learning systems being able to form that. And the context of history of AI, if you could just comment on, there is you said computation X, and there's just some sense where in the 80s and 90s, sort of expert systems represented a very particular computation X.
Yes.
Right? And there's a kind of notion that those efforts didn't pan out.
Right.
But then out of that emerges kind of Wolfram Language, Wolfram Alpha, which is the success. I mean,
Yeah, right. I think those are, in some sense, those efforts were too modest. That is, they were looking at particular areas, and you actually can't do it with a particular area. I mean, like even a problem like natural language understanding, it's critical to have broad knowledge of the world if you want to do good natural language understanding. And you kind of have to bite off the whole problem. Right. If you say we're just going to do the blocks world over here, so to speak, you don't really. It's one of these cases where it's easier to do the whole thing than it is to do some piece of it. You know, one comment to make about sort of the relationship between what we've tried to do and sort of the learning side of AI. You know, in a sense, if you look at the development of knowledge in our civilization as a whole, there was kind of this notion pre-300 years ago or so now, you want to figure something out about the world, you can reason it out. You can do things which just use raw human thought. And then along came sort of modern mathematical science, and we found ways to just sort of blast through that by, in that case, writing down equations. Now we also know we can do that with computation and so on. And so that was kind of a different thing. So when we look at how do we sort of encode knowledge and figure things out, one way we could do it is start from scratch, learn everything. It's just a neural net figuring everything out. But in a sense, that denies the sort of knowledge-based achievements of our civilization. Because in our civilization, we have learned lots of stuff. We've surveyed all the volcanoes in the world. We've done, we've figured out lots of algorithms for this or that. Those are things that we can encode computationally, and that's what we've tried to do. And we're not saying you don't have to start everything from scratch. So in a sense, a big part of what we've done is to try and sort of capture the knowledge of the world in computational form, in computable form. Now, there's also some pieces which were for a long time undoable by computers, like image identification, where there's a really, really useful module that we can add that is those things which actually were pretty easy for humans to do that had been hard for computers to do. I think the thing that's interesting that's emerging now is the interplay between these things, between this kind of knowledge of the world that is, in a sense, very symbolic, and this kind of sort of much more statistical kind of things like image identification and so on, and putting those together by having this sort of symbolic representation of image identification, that's where things get really interesting, and where you can kind of symbolically represent patterns of things and images and so on. I think that's kind of a part of the path forward, so to speak.
Yeah. So the machine learning is not, in my view, I think the view of many people, is not anywhere close to building the kind of wide world of computable knowledge that Wolfram Language have built, but because you have a kind of you've done the incredibly hard work of building this world. Now machine learning can serve as tools to help you explore that world. And that's what you've added. I mean, with the version 12, right? You added a few. I was seeing some demos. It looks amazing.
Right. I mean, I think it's sort of interesting to see the sort of once it's computable, once it's in there, it's running in sort of a very efficient computational way. But then there's sort of things like the interface of how do you get there? How do you do natural language understanding to get there? How do you pick out entities in a big piece of text or something? That's actually a good example right now is our NLP-NLU loop, which is we've done a lot of stuff, natural language understanding, using essentially not learning-based methods, using a lot of, little algorithmic methods, human curation methods, and so on.
In terms of when people try to enter a query and then converting, so the process of converting, NLU defined beautifully as converting their query into a computational language, right, which is a very first of all, super practical definition, a very useful definition, and then also a very clear definition of natural language understanding.
Right. I mean, a different thing is natural language processing, where it's like, here's a big lump of text, go pick out all the cities in that text, for example. And so a good example of, so we do that, we're using modern machine learning techniques. Yeah. And it's actually kind of an interesting process that's going on right now, is this loop between what do we pick up with NLP using machine learning versus what do we pick up with our more kind of precise computational methods in natural language understanding. And so we've got this kind of loop going between those, which is improving both of them.
Yeah, and I think you have some of the state-of-the-art transformers. Like you have BERT in there, I think.
Oh yeah.
So it's cool. So you have integrating all the models. I mean, this is the hybrid thing that people have always dreamed about or talking about. I'm actually just surprised, frankly, that Wolfram Language is not more popular than it already is.
You know,
kind of
it's a complicated issue because it's like it involves, it involves ideas, and ideas are absorbed slowly in the world. I mean, I think that's...
And then there's sort of like we were talking about, there's egos and personalities, and some of the absorption mechanisms of ideas have to do with personalities and the students of personalities and the little social network. So it's interesting how the spread of ideas works.
You know, what's funny with Wolfram Language is that we are, if you say, what market penetration, if you look at I would say, very high end of R&D and sort of the people where you say, wow, that's a really, impressive, smart person, they're very often users of Wolfram Language, very, very often. If you look at the more sort of, it's a funny thing, if you look at the more kind of, I would say, people who are like, oh, we're just plodding away doing what we do, they're often not yet Wolfram Language users. And that dynamic, it's kind of odd that there hasn't been more rapid trickle down, because we've really, the high end, we've really been very successful in for a long time. And but that's partly, I think, a consequence of it's my fault in a sense, because it's kind of, I have a company which really emphasizes sort of creating products and building a sort of the best possible technical tower we can, rather than sort of doing the commercial side of things and pumping it out in sort of the most effective way.
And there's an interesting idea that, perhaps you can make it more popular by opening everything up, sort of the GitHub model. But there's an interesting, I think I've heard you discuss this, that turns out not to work in a lot of cases, like in this particular case, that you want it, that when you deeply care about the integrity, the quality of the knowledge that you're building, that unfortunately you can't distribute that effort.
It's not the nature of how things work. I mean, what we're trying to do is a thing that, for better or worse, requires leadership, and it requires kind of maintaining a coherent vision over a long period of time, and doing not only the cool vision-related work, but also the kind of mundane in the trenches, make the thing actually work.
So how do you build the knowledge? Because that's the fascinating thing. That's the mundane, the fascinating and the mundane is building the knowledge, integrating more data.
Yeah, I mean, that's probably not the most, I mean, the things like get it to work in all these different cloud environments and so on. That's pretty, that's very practical stuff. Have the user interface be smooth, and, have there take only a fraction of a millisecond to do this or that. That's a lot of work. And but, I think it's an interesting thing over the period of time. Wolfram Language has existed basically for more than half of the total amount of time that any computer language has existed. That is, the computer language is maybe 60 years old, give or take, and Wolfram Language is 33 years old. So it's kind of and I think I was realizing recently there's been more innovation in the distribution of software than in the structure of programming languages over that period of time. Yeah. And we've been sort of trying to do our best to adapt to it. And the good news is that we have, because I have a simple private company and so on that doesn't have, a bunch of investors, telling us we got to do this or that, I have lots of freedom in what we can do. And so, for example, we're able to, we have this free Wolfram engine for developers, which is a free version for developers. And we've been, there are site licenses for Mathematica and Wolfram Language at basically all major universities, certainly in the US by now. So it's effectively free to people and all universities in effect. And, we've been doing a progression of things. I mean, different things like Wolfram Alpha, for example, the main website is just a free website.
What is Wolfram Alpha?
Okay. Wolfram Alpha is a system for answering questions where you ask a question with natural language and it'll try and generate a report telling you the answer to that question. So the question could be something like, what's the population of Boston divided by New York compared to New York? And it'll take those words and give you an answer. And that
converts the words into computable
into Wolfram language, actually.
Into Wolfram language,
and computational language, and then computes.
Do you think the underlying knowledge belongs to Wolfram Alpha or to the Wolfram language?
We just call it the Wolfram knowledge base.
Knowledge base.
I mean, that's been a big effort over the decades to collect all that stuff, and more of it flows in every second. So,
can you just pause on that for a second? Like, that's one of the most incredible things. Of course, in the long term, Wolfram language itself is the fundamental thing, but in the amazing sort of short term, the knowledge base is kind of incredible. So what's the process of building that knowledge base? The fact that you, first of all, from the very beginning, that you're brave enough to start to take on the general knowledge base. Mm-hmm. And how do you go from zero to the incredible knowledge base that you have now?
Well, yeah, it was kind of scary at some level. I mean, I had wondered about doing something like this since I was a kid. So it wasn't like I hadn't thought about it for a while.
But most of the brilliant dreamers give up such a difficult engineering notion at some point.
Right. Well, the thing that happened with me, which was kind of, it's a live your own paradigm kind of theory. So basically what happened is I had assumed that to build something like Wolfram Alpha would require sort of solving the general AI problem. That's what I had assumed. And so I kept on thinking about that, and I thought I don't really know how to do that, so I don't do anything. Then I worked on my new kind of science project and sort of exploring the computational universe and came up with things like this principle of computational equivalence, which say there is no bright line between the intelligent and the merely computational. So I thought, look, that's this paradigm I've built. Now now I have to eat that dog food myself, so to speak. I've been thinking about doing this thing with computable knowledge forever, and, let me actually try and do it. And so it was, if my paradigm is right, then this should be possible. But the beginning was certainly, it was a bit daunting. I remember I took the early team to a big reference library, and we're like looking at this reference library, and it's like, my basic statement is our goal over the next year or two is to ingest everything that's in here. And that's, it seemed very daunting, but in a sense, I was well aware of the fact that it's finite. The fact that you can walk into the reference library, it's a big, big thing with lots of reference books all over the place. But it is finite. This is not an infinite, it's not the infinite corridor of, so to speak, of reference library. It's not truly infinite, so to speak. But no, I mean, and then what happened was sort of interesting there was from a methodology point of view was I didn't start off saying, let me have a grand theory for how all this knowledge works. It was like, let's, implement this area, a few hundred areas and so on. That's a lot of work. I also found that, I've been fortunate in that our products get used by sort of the world's experts in lots of areas. And so that really helped because we were able to ask people, the world expert in this or that, we were able to ask them for input and so on. And I found that my general principle was that any area where there wasn't some expert who helped us figure out what to do wouldn't be right. Because our goal was to kind of get to the point where we had sort of true expert level knowledge about everything. And so that, that the ultimate goal is if there's a question that can be answered on the basis of general knowledge in our civilization, make it be automatic to be able to answer that question. And, and now, well, Wolfram Alpha got used in Siri from the very beginning, and it's now also used in Alexa. And so people are kind of getting more of the, they get more of the sense of this is what should be possible to do. I mean, in a sense, the question answering problem was viewed as one of the sort of core AI problems for a long time. I had kind of an interesting experience. I had a friend, Marvin Minsky, who was a well-known AI person from right around here. And I remember when Wolfram Alpha was coming out, it was a few weeks before it came out, I think. I happened to see Marvin, and I said, I should show you this thing we have. It's a question answering system. And he was like, okay, type something in. And it's like, okay, fine. And then he's talking about something different. I said, no, Marvin, this time it actually works. Look at this. It actually works. So he types in a few more things. There's maybe 10 more things. Of course, we have a record of what he typed in, which is kind of interesting. But and then
can you share where his mind was in the testing space? Like what
all kinds of random things. He was just trying random stuff, medical stuff and chemistry stuff and astronomy and so on. And it was like after a few minutes, he was like, "Oh my God, it actually works!" And but that was kind of told you something about the state, what happened in AI, because people had, in a sense, by trying to solve the bigger problem, we were able to actually make something that would work. Now, to be fair, we had a bunch of completely unfair advantages. For example, we already built a bunch of Wolfram Language, which was, very high-level symbolic language. We had, I had the practical experience of building big systems. I have the sort of intellectual confidence to not just sort of give up in doing something like this. I think that it's always a funny thing. I've worked on a bunch of big projects in my life, and I would say that you mention ego, I would also mention optimism, so to speak. I mean, if somebody said this project is going to take 30 years, it would be hard to sell me on that. I'm always in the well, I can kind of see a few years, something's going to happen in a few years. And usually it does. Something happens in a few years, but the tail can be decades long. And that's and from a personal point of view, always the challenge is you end up with these projects that have infinite tails. And the question is, do the tails kind of, do you just drown in kind of dealing with all of the tails of these projects? And that's an interesting sort of personal challenge. And like my efforts now to work on fundamental theory of physics, which I've just started doing, and I'm having a lot of fun with it. But it's kind of, it's kind of making a bet that I can kind of, I can do that as well as doing the incredibly energetic things that I'm trying to do with Wolfram Language and so on.
Mm-hmm.
I mean, the vision, yeah.
And underlying that, I mean, I've just talked for the second time with Elon Musk, and that you two share that quality a little bit of that optimism of taking on basically the daunting, what most people call impossible, and you take it on out of, you can call it ego, you can call it naivety, you can call it optimism, whatever the heck it is, but that's how you solve the impossible things.
Yeah, I mean, look, what happens, and I don't know, in my own case, I progressively got a bit more confident and progressively able to, decide that these projects aren't crazy. But then the other thing is, the other trap that one can end up with is, I've done these projects and they're big. Let me never do a project that's any smaller than any project I've done so far. And that's, and that can be a trap. And often these projects are of completely unknown, their depth and significance is actually very hard to know.
Yeah, on the sort of building this giant knowledge base that's behind Wolfram Language, Wolfram Alpha, what do you think about the internet? What do you think about, for example, Wikipedia, these large aggregations of text that's not converted into computable knowledge? Do you think, if you look at Wolfram Language, Wolfram Alpha, 20, 30, maybe 50 years down the line, do you hope to store all of the sort of Google's dream is to make all information searchable, accessible, but that's really, as defined, it doesn't include the understanding of information.
Right.
Do you hope to make all of knowledge represented within?
I would hope so. That's what we're trying to do.
How hard is that problem? Like closing that gap? What's your sense?
Well, it depends on the use cases. I mean, so if it's a question of answering general knowledge questions about the world, we're in pretty good shape on that right now. if it's a question of representing, like an area that we're going into right now is computational contracts, being able to take something which would be written in legalese. It might even be the specifications for, what should the self-driving car do when it encounters this or that or the other? What should the, whatever. Write that in a computational language and be able to express things about the world. If the creature that you see running across the road is a, thing at this point in the, tree of life, then swerve this way. Otherwise, don't. Those kinds of things.
Are there ethical components? When you start to get to some of the messy human things, are those encodable into computable knowledge?
Well, I think that it is a necessary feature of attempting to automate more in the world that we encode more and more of ethics in a way that gets sort of quickly, is able to be dealt with by computer. I mean, I've been involved recently. I sort of got backed into being involved in the question of automated content selection on the internet. So, the Facebooks, Googles, Twitters, how do they rank the stuff they feed to us humans, so to speak? And the question of what should never be fed to us, what should be blocked forever, what should be upranked, and what are the kind of principles behind that? And what a bunch of different things I realized about that. But one thing that's interesting is being able, in effect, you're building sort of an AI ethics. You have to build an AI ethics module, in effect, to decide, is this thing so shocking I'm never going to show it to people? Mm-hmm. Is this thing so whatever? And I did realize in thinking about that, there's not going to be one of these things. It's not possible to decide, or it might be possible, but it would be really bad for the future of our species if we just decided there's this one AI ethics module and it's going to determine the practices of everything in the world, so to speak. And I kind of realized one has to sort of break it up, and that's an interesting societal problem of how one does that, and how one sort of has people sort of self-identify for, I'm buying in the case of just content selection, it's sort of easier because it's like it's for an individual. It's not something that kind of cuts across sort of societal boundaries. But
it's a really interesting notion of, I heard you describe, I really like it, sort of, maybe sort of have different AI systems that have a certain kind of brand that they represent, essentially. Right. You could have like I don't know, whether it's conservative or liberal, and then libertarian, and there's an Randian objectivist AI ethics system, and different ethical it's almost encoding some of the ideologies which we've been struggling. I come from the Soviet Union. That didn't work out so well with the ideologies that worked out there, and so you have, but everybody purchased that particular ethics system.
Indeed,
and in the same, I suppose, could be done encoded. That system could be encoded into computational knowledge and allow us to explore in the realm of in the digital space. That's a really exciting possibility. Right. So, are you playing with those ideas in Wolfram Language?
Yeah. I mean, Wolfram Language has sort of the best opportunity to kind of express those essentially computational contracts about what to do. Now, there's a bunch more work to be done to do it in practice for, deciding is this a credible news story? What does that mean? Or whatever else you're going to pick. I think that's the question of exactly what we get to do with that is, for me, it's kind of a complicated thing because there are these big projects that I think about, like, find the fundamental theory of physics. Okay, that's box number one, right? Box number two, solve the AI ethics problem in the case of, figure out how you rank all content, so to speak, and decide what people see. That's kind of a box number two, so to speak. Yeah. These are big projects. And I think...
What do you think is more important? The fundamental nature of reality, or...
Depends who you ask. It's one of these things that's exactly like, what's the ranking, right? It's the ranking system. Yeah. It's like whose module do you use to rank that? If you and I think
but having multiple modules is a really compelling notion to us humans. That in a world where there's not clear that there's a right answer, perhaps you have systems that operate under different. How would you say it? I mean,
It's different value systems, basically.
Different value systems.
I mean, I think, in a sense, I'm not really a politics-oriented person, but in the kind of totalitarianism, it's kind of like you're going to have this system, and that's the way it is. I mean, kind of the concept of sort of a market-based system where you have, okay, I as a human, I'm going to pick this system. I as another human, I'm going to pick this system. I mean, that's, in a sense, this case of automated content selection is a non-trivial, but it is probably the easiest of the AI ethics situations, because it is each person gets to pick for themselves, and there's not a huge interplay between what different people pick. By the time you're dealing with other societal things like, what should the policy of the central bank be or something?
Yeah, or healthcare system or something, all those kind of centralized kind of things. Yeah.
Right. Well, I mean, healthcare, again, has the feature that at some level, each person can pick for themselves, so to speak. I mean, whereas there are other things where there's a necessary public health, as one example, where that's not, where that doesn't get to be, something which people can, what they pick for themselves, they may impose on other people, and then it becomes a more non-trivial piece of sort of political philosophy.
Of course, the central banking system, some would argue we need to move into digital currency and so on, and Bitcoin and ledgers and so on. So
yes,
there's a lot of...
We've been quite involved in that. And that's where, that's sort of the motivation for computational contracts, in part, comes out of, this idea, we can just have this autonomously executing smart contract. The idea of a computational contract is just to say, have something where all of the conditions of the contract are represented in computational form. So in principle, it's automatic to execute the contract. And I think that's, that will surely be the future of, the idea of legal contracts written in English or legalese or whatever, and where people have to argue about what goes on is surely not... we have a much more streamlined process if everything can be represented computationally and the computers can kind of decide what to do. I mean, ironically enough, old Gottfried Leibniz back in the, 1600s was saying exactly the same thing. But he had, his pinnacle of technical achievement was this brass 4-function mechanical calculator thing that never really worked properly, actually. Mm-hmm. So he was like 300 years too early for that idea. But now, that idea is pretty realistic, I think. And, you ask how much more difficult is it than what we have now in Wolfram Language to express, I call it symbolic discourse language, being able to express sort of everything in the world in kind of computational symbolic form. I think it is absolutely within reach. I mean, I think it's I don't know, maybe I'm just too much of an optimist, but I think it's a limited number of years to have a pretty well built out version of that will allow one to encode the kinds of things that are relevant to typical legal contracts and these kinds of things.
So the idea of symbolic discourse language, can you try to define the scope of what of what it is?
So we're having a conversation. It's a natural language. Can we have a representation of the sort of actionable parts of that conversation in a precise computable form so that a computer could go do it?
And not just contracts, but really sort of some of the things we think of as common sense, essentially, even just like basic notions of human life.
Well, I mean, things like, I'm getting hungry and want to eat something, right? That's something we don't have a representation. In Wolfram Language right now, if I was like, I'm eating blueberries and raspberries and things like that, and I'm eating this amount of them, we know all about those kinds of fruits and plants and nutrition content and all that kind of thing. But the I want to eat them part of it is not covered yet. And that, and
you need to do that in order to have a complete symbolic discourse language, to be able to have a natural language conversation.
Right. To be able to express the kinds of things that say, if it's a legal contract, it's, the parties desire to have this and that. And that's a thing like I want to eat a raspberry or something. But
isn't this, just telling you said it's centuries old, this dream.
Yes.
But it's also the more near term, the dream of Turing and formulating the Turing test.
Yes.
So do you think that's the ultimate test of creating something special? Because we said...
I don't know. I think by special, look, if the test is, does it walk and talk like a human? Well, that's just the talking like a human. But the answer is, it's an okay test. If you say, is it a test of intelligence? People have attached the Wolfram Alpha API to, Turing test bots. Mm-hmm. And those bots just lose immediately, because all you have to do is ask it 5 questions that, are about really obscure, weird pieces of knowledge, and it's just trot them right out. Mm-hmm. And you say, that's not a human, right? It's a different thing. It's achieving a different,
right now, but it's, I would argue not. I would argue it's not a different thing. It's actually legitimately, Wolfram Alpha is legitimately Wolfram Language, I think, is legitimately trying to solve the intent of the Turing test.
Perhaps the intent. Yeah, perhaps the intent. I mean, it's actually kind of fun. Alan Turing had tried to work out, he thought about taking Encyclopedia Britannica and, making it computational in some way. And he estimated how much work it would be. And actually, I have to say he was a bit more pessimistic than the reality. We did it more efficiently than that.
But to him, that represented...
So I mean, he was on the
monumental task.
Yeah, right. He had the same idea. I mean, it was, we were able to do it more efficiently because we had layers of automation that he, I think, hadn't. It's hard to imagine those layers of abstraction that end up being built up.
But to him, it represented like an impossible task, essentially.
Well, he thought it was difficult. He thought it was, maybe if he'd lived another 50 years, he would have been able to do it. I don't know.
In the interest of time, easy questions.
Go for it.
What is intelligence? You talked about...
I love the way you say easy questions.
Yeah. You talked about sort of Rule 30 and Cellular Automata humbling your sense of human beings having a monopoly on intelligence. But in retrospect, just looking broadly now with all the things you learned from computation, what is intelligence? How does intelligence arise?
Yeah, I don't think there's a bright line of what intelligence is. I think intelligence is at some level just computation, but for us, intelligence is defined to be computation that is doing things we care about. And, that's a very special definition. It's a very, when you try and make it you try and say, well, intelligence is this, it's problem solving, it's doing general this, it's doing that, this, that, and the other thing. It's operating within a human environment type thing. Okay, that's fine. If you say, well, what's intelligence in general? I think that question is totally slippery and doesn't really have an answer. As soon as you say, what is it in general? It quickly segues into this is just computation, so to speak.
But in a sea of computation, how many things, if we were to pick randomly, is your sense, would have the kind of impressive to us humans levels of intelligence, meaning it could do a lot of general things that are useful to us humans?
Right. Well, according to the principle of computational equivalence, lots of them. I mean, in if you ask me just in cellular automata or something, I don't know, it's maybe 1%, a few percent achieve. It varies actually. It's a little bit as you get to slightly more complicated rules, the chance that there'll be enough stuff there to sort of reach this kind of equivalence point. It makes it maybe 10, 20% of all of them. So it's very disappointing, really. I mean, it's kind of like, we think there's this whole long sort of biological evolution, kind of intellectual evolution cultural evolution that our species has gone through. It's kind of disappointing to think that hasn't achieved more, but it has achieved something very special to us. It just hasn't achieved something generally more, so to speak.
But what do you think about this extra, feels like human thing of subjective experience, of consciousness? What is consciousness?
Well, I think it's a deeply slippery thing, and I'm always wondering what my cellular automata feel. I mean,
what do they feel? Now, you're wondering as an observer.
Yeah. Right. Who's to know? I mean, I think that Do
you think? Sorry to interrupt. Do you think consciousness can emerge from computation?
Yeah. I mean, everything, whatever you mean by it, it's going to be. Look, I have to tell a little story. I was at an AI ethics conference fairly recently, and people were. I think maybe I brought it up, but I was like talking about rights of AIs. Mm-hmm. When will AIs have? When should we think of AIs as having rights? When should we think that it's immoral to destroy the memories of AIs, for example? Those kinds of things, and some actually philosopher in this case. It's usually the techies who are the most naive, but in this case, it was a philosopher who sort of piped up and said, "Well, the AIs will have rights when we know that they have consciousness." And I'm like, good luck with that. I mean, it's a very circular thing. You'll end up saying this thing that has sort of, when you talk about it having subjective experience, I think that's just another one of these words that doesn't really have there's no ground truth definition of what that means.
By the way, I would say I do personally think there'll be a time when AI will demand rights, and I think they'll demand rights when they say they have consciousness, which is not a circular definition.
Well, fair enough.
But
it may have been actually a human thing where the humans encouraged it and said, basically, we want you to be more like us because we're going to be, interacting with you. And so we want you to be sort of very Turing test like, just like us. Yeah. And it's like, yeah, we're just like you. And we want to vote too, or whatever. Which is it's an interesting thing to think through in a world where consciousnesses are not counted like humans are. That's a complicated business.
So in many ways, you've launched quite a few ideas, revolutions that could, in some number of years, have huge amount of impact, sort of more than they had or even had already. That might be, to me, cellular automata is a fascinating world that I think could potentially, beside the discussion of fundamental laws of physics, the idea of computation might be transformational to society in a way we can't even predict yet. But it might be years away.
That's true. I think you can kind of see the map. Actually, it's not mysterious. The fact is that this idea of computation is sort of it's a big paradigm that lots and lots of things are fitting into, and it's kind of like you talk about I don't know, this company, this organization has momentum in what it's doing. We talk about these things that we've internalized these concepts from Newtonian physics and so on. In time, things like computational irreducibility will become as actually, I was amused recently. I happened to be testifying at the U.S. Senate, and so I was amused that the term computational irreducibility is now can be, it's on the congressional record and being repeated by people.
I love it.
In those kinds of settings. But that's only the beginning, because computational irreducibility, for example, will end up being something really important for. It's kind of a funny thing that one can kind of see this inexorable phenomenon. It's, as more and more stuff becomes automated and computational and so on, so these core ideas about how computation work necessarily become more and more significant. And I think one of the things for people like me who like kind of trying to figure out sort of big stories and so on, is one of the bad features is it takes unbelievably long time for things to happen on a human time scale. The time scale of history, it all looks instantaneous.
Blink of an eye. But Let me ask the human question. Do you ponder mortality, your own mortality? Of
course I do. Yeah, every sense. I've been interested in that for, the big discontinuity of human history will come when one achieves effective human immortality. And that's going to be the biggest discontinuity in human history.
If you could be immortal, would you choose to be?
Oh, yeah, I'm having fun.
Yeah. Do you think it's possible that mortality is the thing that gives everything meaning and makes it fun?
Yeah, that's a complicated issue, right? The way that human motivation will evolve when there is effective human immortality is unclear. If you look at sort of, you look at the human condition as it now exists, and you change that, you change that knob, so to speak, it doesn't really work. the human condition as it now exists has, mortality is kind of something that is deeply factored into the human condition as it now exists. And I think that is indeed an interesting question, is, from a purely selfish, I'm having fun point of view, so to speak, it's easy to say, hey, I could keep doing this forever. There's an infinite collection of things I'd like to figure out. But I think what the future of history looks like in a time of human immortality is an interesting one. I mean, my own view of this, I was kind of unhappy about that, because I was kind of, it's like, okay, forget sort of biological form, everything becomes digital, everybody is, it's the giant, the cloud of a trillion souls type thing. And then that seems boring, because it's like play video games for the rest of eternity type thing. Mm-hmm. But what I think I got less depressed about that idea on realizing that if you look at human history and you say, what was the important thing? The thing people said was, this is the big story at any given time in history. It's changed a bunch. And whether it's, why am I doing what I'm doing? Well, there's a whole chain of discussion about, well, I'm doing this, because of that. And a lot of those becauses would have made no sense 1,000 years ago. Absolutely no sense.
So the interpretation of the human condition, even the meaning of life, changes over time.
Well, I mean, why do people do things? It's if you say whatever. I mean, the number of people in, I don't know, doing, number of people at MIT who say they're doing what they're doing for the greater glory of God is probably not that large.
Yeah.
Whereas if you go back 500 years, you'd find that a lot of people who are doing kind of creative things, that's what they would say.
So today, because you've been thinking about computation so much and been humbled by it, what do you think is the meaning of life?
Well, it's that's a thing where I don't know what meaning. I mean, my attitude is, I do things which I find fulfilling to do. I'm not sure that I can necessarily justify, each and everything that I do on the basis of some broader context. I mean, I think that for me, it so happens that the things I find fulfilling to do, some of them are quite big, some of them are much smaller. They're things that I've not found interesting earlier in my life, and I now found interesting. Like I got interested in like education and teaching people things and so on, which I didn't find that interesting when I was younger. Can I justify that in some big global sense? I don't think. I mean, I can describe why I think it might be important in the world, but I think my local reason for doing it is that I find it personally fulfilling, which I can't, explain on a sort of. It's just like this discussion of things like AI ethics. Is there a ground truth to the ethics that we should be having? I don't think I can find a ground truth to my life any more than I can suggest a ground truth for kind of the ethics for the whole of civilization. And I think that's it would be a it's sort of a, I think I'm at different times in my life, I've had different kind of goal structures and so on. Although
from your perspective, you're local, you're just a cell in the cellular automata. But in some sense, I find it funny from my observation is I kind of, it seems that the universe is using you to understand itself in some sense. You're not aware of it.
Yeah, well, right. Well, if it turns out that we reduce sort of all of the universe to some simple rule, everything is connected, so to speak. And so it is inexorable in that case that, if I'm involved in finding how that rule works, then, then that's then it's inexorable that the universe set it up that way. But I think, one of the things I find a little bit, in this goal of finding fundamental theory of physics, for example, if indeed we end up as this sort of virtualized consciousness, the disappointing feature is people will probably care less about the fundamental theory of physics in that setting than they would now, because, gosh, it's like, what the machine code is down below underneath this thing is much less important if you're virtualized, so to speak. And I think although I think my own personal, you talk about ego, I find it just amusing that, if you're imagining that sort of virtualized consciousness, like what does the virtualized consciousness do for the rest of eternity? Well, you can explore, the video game that represents the universe as the universe is, or you can go off that reservation and go and start exploring the computational universe of all possible universes.
Yeah.
And so in some vision of the future of history, it's like the disembodied consciousnesses are all sort of pursuing things like my new kind of science sort of for the rest of eternity, so to speak. And that ends up being the kind of the thing that represents the future of kind of the human condition.
I don't think there's a better way to end it, Stephen. Thank you so much. It's a huge honor talking today. Thank you so much.
This was great. You did very well.
Thanks for listening to this conversation with Stephen Wolfram, and thank you to our sponsors, ExpressVPN and Cash App. Please consider supporting the podcast by getting ExpressVPN at expressvpn.com/LexPod and downloading Cash App and using code LexPodcast. If you enjoy this podcast, subscribe on YouTube, review it with 5 stars on Apple Podcast, support it on Patreon, or simply connect with me on Twitter at Lex Fridman. And now, let me leave you with some words from Stephen Wolfram. It is perhaps a little humbling to discover that we as humans are in effect computationally no more capable than the cellular automata with very simple rules. But the principle of computational equivalence also implies that the same is ultimately true of our whole universe. So, while science has often made it seem that we as humans are somehow insignificant compared to the universe, the principle of computational equivalence now shows that in a certain sense, we're at the same level. For the principle implies that what goes on inside us can ultimately achieve just the same level of computational sophistication as our whole universe. Thank you for listening, and hope to see you next time.